Welcome, dear friend. I'm so glad you're here with me tonight. Find yourself a comfortable position, let your body sink into wherever you're resting, and allow your breathing to slow into a gentle, easy rhythm. We're about to embark on the most extraordinary journey imaginable, a voyage through the complete history of our planet Earth, all 4.5 billion years of it. From the very first moments of its fiery birth to the world you know today, with its blue oceans, green forests, and endless diversity of life. There's something deeply comforting about understanding where we come from. Our Earth has been through so much, has transformed in ways that seem almost impossible, and yet here it is, still spinning, still nurturing life, still providing us with everything we need. As you listen to this story, let the vast stretches of time wash over you like gentle waves. There's no need to memorize anything or keep track of dates. Simply let the narrative carry you. Let the images form in your mind, and if sleep finds you along the way, that's perfectly wonderful. The story of Earth will still be here, written in the rocks beneath your feet and the air you breathe. To truly understand the birth of our planet, we must first step back even further, to a time before Earth existed, before our sun had ignited, before our entire solar system had taken shape. We must travel to the cosmic environment that made Earth possible in the first place. Picture the Milky Way galaxy as it appeared roughly 5 billion years ago. This vast spiral of stars, gas and dust had already been in existence for about 8 or 9 billion years by that point. Generations of stars had lived and died within its graceful arms, and this detail is crucial to our story. You see, the very first stars in the universe, those ancient pioneers that ignited just a few 100 million years after the Big Bang, were composed almost entirely of hydrogen and helium, the simplest elements. They contain none of the heavier elements that make rocky planets like Earth possible. No carbon, no oxygen, no silicon, no iron. But stars are cosmic alchemists. Deep within their cores, under temperatures and pressures almost beyond comprehension, they forge heavier elements through nuclear fusion. Hydrogen atoms combine to form helium. Helium atoms fuse to create carbon. Carbon becomes oxygen. And on the process continues, building up the periodic table element by element. When massive stars exhaust their fuel and explode as supernova, they scatter these newly created elements across space, enriching the surrounding gas clouds with the raw materials for planets and eventually for life itself. By the time our corner of the Milky Way was preparing to give birth to our solar system, countless generations of stars had lived their lives and contributed their elemental gifts to the cosmic reservoir. The gas cloud that would become our solar neighbourhood was no longer pristine hydrogen and helium. It was seasoned with oxygen, carbon, nitrogen, silicon, iron, and dozens of other elements, all cooked up in the hearts of long-dead stars. As the astronomer Carl Sagan so beautifully expressed, we are made of star stuff, and so is our Earth. Now let your mind drift to a particular region within one of the Milky Way's spiral arms, a place where gas and dust had accumulated into a vast molecular cloud. These clouds are among the coldest places in the universe, with temperatures hovering just a few degrees above absolute zero. They're also incredibly diffuse by earthly standards. If you could somehow transport yourself into the densest part of such a cloud, you might not even notice you were inside anything at all. The particles are spread so thin that the cloud would appear as a near-perfect vacuum compared to the air you're breathing right now. And yet, across the immense scales of space, these clouds contain enormous amounts of material. The molecular cloud that spawned our solar system likely stretched across dozens of light years and contained enough gas and dust to form thousands of stars. For millions of years, this cloud drifted through the galaxy, its particles moving in slow, lazy paths, held together loosely by their collective gravity, but not dense enough to collapse into anything more structured. Then something happened to disturb this peaceful equilibrium. We don't know exactly what triggered the collapse of our particular region of the cloud. Perhaps a nearby supernova sent a shockwave rippling through the gas, compressing it just enough to tip the balance. Perhaps the cloud simply drifted into a denser region of the galaxy where gravitational perturbations became stronger. Or perhaps the slow, patient accumulation of material over millions of years finally reached a critical threshold. Whatever the cause, roughly 4.6 billion years ago, a portion of this molecular cloud began to collapse under its own gravity. At first, the collapse was almost imperceptibly slow. Particles that had been drifting aimlessly began to fall inward, drawn toward the growing concentration of mass at the cloud center. As more material accumulated, the gravitational pull strengthened and the collapse accelerated. What had begun as a gentle settling became an inexorable inward rush. As the cloud collapsed, something fascinating happened. Any tiny bit of rotation the original cloud possessed became amplified, much like a figure skater spinning faster when they pull their arms close to their body. This is the conservation of angular momentum, one of the fundamental principles of physics, and it shaped the very structure of our solar system. The collapsing cloud began to spin faster and faster, and this rotation prevented all the material from falling directly into the center. Instead, the cloud flattened into a rotating disk with a dense, hot concentration of gas at its center. This central concentration would become our sun. As more and more material piled onto it, the pressure and temperature at its core climbed higher and higher. Atoms were squeezed together with increasing force. The proto-sun began to glow, not yet from nuclear fusion, but simply from the heat generated by gravitational compression. It was a star in the making, a stellar embryo wrapped in a cocoon of gas and dust. The disk of material surrounding this infant sun is what scientists call a protoplanetary disk, or sometimes a solar nebula. It was within this disk that Earth and all the other planets would form. Picture it as a vast, flattened cloud of gas and dust, rotating around the central proto-sun, extending outward for billions of kilometers. The disk was not uniform. Closer to the proto-sun, where temperatures were highest, only materials with high melting points could exist in solid form, metals and rocky silicates. Further out, beyond a boundary called the frost line or snow line, it was cold enough for water, ammonia, methane, and other volatile compounds to freeze into solid ice. This temperature gradient would prove crucial in determining what kinds of planets formed where. In the inner solar system, where Earth would eventually take shape, the building blocks were primarily rocky and metallic. In the outer solar system, abundant ices joined the mix, allowing planets to grow much larger by incorporating these additional materials. Within the swirling disk, the first steps toward planet formation were remarkably humble. Tiny grains of dust, each smaller than a grain of sand, began to stick together when they collided. This process, called accretion, started almost immediately after the disk formed. The dust grains were coated with thin layers of ice or organic compounds that acted like glue, allowing them to clump together rather than bouncing apart. Over thousands of years, these clumps grew from microscopic specks to pebble-sized objects, then to boulder-sized rocks. As these objects grew larger, their gravity began to play a more significant role. The bigger chunks could attract smaller ones, accelerating their growth. Collisions became more energetic as the objects grew, and not all of them resulted in sticking. Sometimes impact would shatter both objects into fragments. But on average, growth won out over destruction, and the objects continued to increase in size. After perhaps 100,000 years, the disk was populated by countless objects, ranging from dust grains to bodies several kilometers across. These kilometer-sized objects are called planetesimals, and they represent a crucial stage in planet formation. Planetesimals were large enough that their gravity could significantly influence their interactions with other bodies. They swept up smaller debris, collided and merged with each other, and gradually cleared out the material in their orbital neighborhoods. The region of the disk where Earth would form, roughly 150 million kilometers from the proto-sun, was a busy place during this era. Countless planetesimals jostled for position, their orbits crossing and recrossing, leading to frequent collisions. Some of these collisions were gentle enough to result in mergers. Others were violent enough to shatter both bodies. The outcome of each collision depended on the relative speeds and sizes of the objects involved, as well as the angle at which they met. Over millions of years, a few planetesimals in Earth's region managed to grow significantly larger than their neighbours. These fortunate few had won an early advantage, perhaps through a series of lucky collisions, and their greater gravity allowed them to grow even faster. Scientists call these objects planetary embryos or protoplanets. They ranged in size from a few hundred to a few thousand kilometres in diameter, comparable to the largest asteroids we see today. By about 4.5 billion years ago, the inner solar system contained perhaps 50 to 100 of these protoplanets, along with countless smaller planetesimals and debris. The proto-sun had by this point ignited nuclear fusion in its core and become a true star, flooding the solar system with light and heat. The intense radiation and powerful solar wind from the young sun began to blow away the remaining gas in the disk, leaving behind only the solid bodies that had formed. What followed was an era of giant impacts, a chaotic period lasting perhaps 50 to 100 million years, during which the protoplanets collided with each other in a violent process of consolidation. The inner solar system was like a cosmic demolition derby, with Mars-sized and larger bodies smashing into each other at tremendous speeds. Each collision released enormous amounts of energy, melting and partially vaporizing the impacting bodies, mixing their materials together, and gradually building up larger and larger worlds. Earth grew through this process of repeated giant impacts. Each collision added mass to our growing planet, while simultaneously releasing enough energy to melt much of its surface. The young Earth was not the cool blue world we know today. It was a hellscape of molten rock, its surface glowing orange and red, with no solid ground anywhere to be found. Oceans of magma covered the entire planet, thousands of kilometers deep in places. But even in this violent environment, the processes that would shape Earth's future were already at work. The molten state of the early Earth allowed heavy elements like iron and nickel to sink toward the center, while lighter rocky materials floated toward the surface. This separation, called differentiation, created Earth's layered internal structure, with a dense metallic core surrounded by a rocky mantle and crust. The core would eventually generate Earth's magnetic field, which would prove essential for protecting the atmosphere and making life possible. As you listen to this description of Earth's violent birth, let your body remain relaxed and at ease. These events happened so long ago, in a time so remote from our own experience, that they almost seem like a dream. The chaos and violence of that era have long since faded, replaced by the gentle, nurturing world we know today. But understanding where we came from helps us appreciate how remarkable our planet truly is. Every atom in your body, every breath you take, every drop of water you drink, all of it traces back to this tumultuous beginning, to a disk of gas and dust swirling around a newborn star, to countless collisions and mergers that gradually assembled the world we call home. The solar nebula phase of our solar system's history lasted only a few million years, a mere eye blink in cosmic terms. But in that brief window, the fundamental architecture of our planetary system was established. The Sun claimed the vast majority of the original cloud's mass, about 99.8% of it. The planets, moons, asteroids, and comets that make up the rest of the solar system formed from the remaining 0.2%. And among all these worlds, one small rocky planet in the inner solar system would eventually become something truly special. A world where matter would organize itself into living things, where consciousness would emerge, where beings would one day look up at the stars and wonder about their origins. That world was Earth, and its story was just beginning. Section 2, Birth from Chaos, the Formation of Earth. Let your mind now focus on this one particular region of the young solar system, about 150 million kilometers from the Sun, where countless rocky fragments were slowly assembling into what would become our home world. The process of Earth's formation was neither quick nor simple. It unfolded over tens of millions of years through countless collisions, each one adding to the growing mass of our planet. In the earliest stages, Earth was not a single body, but rather a swarm of planetesimals, rocky objects ranging from pebbles to mountains in size, all orbiting the Sun in roughly the same region of space. These objects were the building blocks of our planet, and they were remarkably diverse in composition. Some were rich in iron and nickel, the materials that would eventually form Earth's core. Others were dominated by silicate minerals, the stuff of rocks and mountains. Still others contained significant amounts of water, locked away in hydrated minerals or frozen as ice. The collisions between these planetesimals were frequent and varied in their intensity. When two small objects met at low speeds, they might gently stick together, their combined gravity holding them as one. When larger objects collided at higher speeds, the impacts released tremendous energy, melting rock and sometimes partially vaporizing both bodies. The debris from these violent collisions would eventually fall back together, reassembling into a larger object that incorporated material from both original bodies. Through this process of accretion, certain planetesimals grew faster than others. Perhaps they started out slightly larger, or perhaps they occupied orbits that brought them into contact with more material. Whatever the reason, these fortunate few became planetary embryos, objects large enough that their gravity dominated their local environment. They swept up smaller debris like cosmic vacuum cleaners, growing larger with each passing millennium. Earth's growth accelerated as it became more massive. Gravity is a patient but relentless force, and the more mass an object accumulates, the stronger its gravitational pull becomes. A planetary embryo twice as massive as its neighbour doesn't just have twice the gravity, it has a much larger sphere of influence, a region of space where its gravity can capture passing objects. This meant that the largest embryos grew fastest, a phenomenon scientists call runaway accretion. By about 4.5 billion years ago, the region of space where Earth was forming contained several large planetary embryos, each comparable in size to the Moon or Mars. These protoplanets had swept up most of the smaller debris in their orbital neighbourhoods, but they were not yet finished growing. Their orbits were not perfectly stable, and gravitational interactions between them caused these orbits to shift and change over time. Inevitably, the paths of different protoplanets began to cross. What followed was an era of truly catastrophic collisions, impacts between world-sized objects travelling at speeds of several kilometres per second. The energy released in such collisions is almost beyond comprehension. When two Mars-sized objects collide, the impact releases more energy than 1 billion nuclear weapons detonating simultaneously. Rock is not just melted, but vaporized. The colliding bodies are completely disrupted, their materials mixing together in a cloud of superheated debris before gravity pulls everything back together into a new, larger world. Earth experienced many such giant impacts during its formation. Each one added mass to our growing planet, while simultaneously resetting its surface to a molten state. The young Earth had no solid crust, no oceans, no atmosphere in the modern sense. It was a world of magma, its surface glowing with the heat of recent impacts and the ongoing release of internal heat from gravitational compression and radioactive decay. One of the most important processes occurring during this time was differentiation, the separation of Earth's materials into distinct layers based on their density. In the completely molten state of the early Earth, heavy materials like iron and nickel sank toward the centre, while lighter silicate minerals floated toward the surface. This process happened relatively quickly in geological terms, probably within the first few tens of millions of years of Earth's formation. The sinking of iron to form Earth's core released enormous amounts of gravitational energy, which was converted to heat. This heat, combined with the energy from impacts and the decay of radioactive elements, kept the early Earth in a largely molten state for millions of years. The core that formed during this period would prove crucial for Earth's future habitability. The liquid outer core, composed primarily of iron and nickel, with some lighter elements mixed in, would eventually generate Earth's magnetic field through a process called the geodynamo. As Earth grew through successive impacts, it also accumulated the raw materials for its future atmosphere and oceans. Many of the planetesimals that collided with the growing Earth contained volatile compounds, substances that easily vaporize at relatively low temperatures. Water was among the most important of these volatiles, along with carbon dioxide, nitrogen, and various sulfur compounds. When these volatile-rich objects struck the molten Earth, their volatile contents were released as gases, forming a thick, steamy atmosphere around the young planet. This early atmosphere was nothing like the air we breathe today. It was dominated by water vapour, carbon dioxide, and nitrogen, with smaller amounts of hydrogen sulfide, sulfur dioxide, and other noxious gases. The surface pressure may have been tens or even hundreds of times greater than today's atmospheric pressure. The temperature at the surface, kept high by the ongoing bombardment and the greenhouse effect of the thick atmosphere, was far too hot for liquid water to exist. Let yourself imagine this alien world, this version of Earth so different from the one we know. Picture a globe entirely covered in glowing orange magma, its surface constantly churned by convection currents, bringing heat from the interior. Above this hellish landscape hangs a thick, hazy atmosphere, tinged orange and red by suspended particles of rock vapour and sulphurous compounds. The sky's not blue, but a murky, oppressive ceiling of clouds and haze. There is no day and night as we know them, no sunrise or sunset, just the constant, angry glow of the molten surface illuminating the atmosphere from below. And yet, even in this hostile environment, the seeds of Earth's future were being planted. The differentiation of the core was setting the stage for the magnetic field that would one day protect life from harmful solar radiation. The outgassing of volatiles was creating the raw materials for oceans and atmosphere. The heat being generated and released was driving the geological processes that would eventually create continents and ocean basins. Everything that would make Earth special was already present in potential, waiting for the violence to subside so that gentler processes could begin. The growth of Earth through accretion was not a smooth, continuous process. There were periods of relative calm punctuated by sudden, dramatic impacts. Each major collision set back the clock on surface cooling, remelting whatever thin crust might have begun to form and adding fresh heat to the interior. But as time passed and Earth swept up more and more of the debris in its orbital neighbourhood, the frequency of major impacts began to decline. By about 4.5 billion years ago, Earth had reached approximately its current mass. It was the largest of the rocky planets in the inner solar system, more massive than Mercury, Venus or Mars. This size would prove important for Earth's future. A larger planet has stronger gravity, which helps it retain a substantial atmosphere. A larger planet also has more internal heat, which drives geological activity like volcanism and plate tectonics. And a larger planet cools more slowly, allowing these geological processes to continue for billions of years. But Earth's formation story was not yet complete. The most dramatic event in our planet's early history was still to come. A collision so massive and so transformative that it would create Earth's constant companion in the sky, the Moon. This event, known as the Giant Impact or sometimes the Big Splash, would reshape Earth in fundamental ways and set the stage for everything that followed. The impactor, sometimes called Theia, after the Greek Titaness, who was the mother of the moon goddess Selene, was itself a fully formed protoplanet, roughly the size of Mars. Theia had been growing in its own region of the inner solar system, accumulating mass through the same processes that had built Earth. But its orbit was not stable. Gravitational interactions with Earth and other bodies gradually shifted Theia's path until inevitably it crossed Earth's orbit at exactly the wrong moment. The collision between Earth and Theia was the most energetic event in our planet's history. The two worlds met at a glancing angle, with Theia striking Earth's surface at a speed of perhaps 10 to 15 kilometers per second. The impact released energy equivalent to billions of hydrogen bombs, enough to completely melt both bodies and vaporize a significant portion of their combined mass. In the immediate aftermath of the impact, there was no Earth as we would recognize it. Instead, there was a spinning cloud of superheated rock vapor, liquid magma, and solid debris, all swirling together in a chaotic maelstrom. The temperatures at the center of this cloud exceeded 10,000 degrees, hot enough to vaporize any known material. The entire mass was rotating rapidly. The angular momentum of both original bodies now combined into a single spinning system. Over the following hours and days, this cloud began to sort itself out. The densest material, primarily iron from the cores of both Earth and Theia, sank toward the center, merging to form a new, larger core. Lighter silicate materials spread outward, some falling back to form the mantle of the reconstituted Earth, others remaining in orbit around the central mass. The material that stayed in orbit would become the Moon. Initially, this material formed a disk around the still molten Earth, similar in some ways to the rings of Saturn, but far more massive and composed of liquid and vaporized rock rather than ice. Within this disk, the same processes of accretion that had built the planets began again on a smaller scale. Droplets of molten rock collided and merged, gradually assembling into larger and larger bodies. Within perhaps a few thousand years, most of the orbiting material had coalesced into a single large body, the Moon. The newborn Moon was much closer to Earth than it is today, perhaps only about 25,000 kilometers away, compared to its current distance of nearly 400,000 kilometers. At that distance, the Moon would have appeared enormous in Earth's sky, perhaps 20 times larger than it appears today. The close proximity of the Moon had profound effects on both bodies. Tidal forces between Earth and Moon were immensely powerful, causing both bodies to flex and deform as they rotated. This tidal heating added even more energy to the already molten Earth and kept the Moon in a molten state as well. The Moon's surface was covered in a global magma ocean, just like Earth's. Over time, tidal interactions between Earth and Moon caused the Moon to slowly spiral outward, while Earth's rotation gradually slowed. This process continues to this day. The Moon moves about 3.8 centimeters farther from Earth each year, and Earth's day grows longer by about 1.4 milliseconds per century. 4 billion years ago, Earth's day was only about 6 hours long, and the Moon loomed large and close in the sky. The formation of the Moon had several important consequences for Earth's future. The Moon stabilizes Earth's axial tilt, preventing the wild swings in orientation that would otherwise cause extreme climate variations. The The moon's gravity drives ocean tides, which may have played a role in the origin of life, by creating tidal pools where complex chemistry could occur. And the giant impact that created the moon thoroughly mixed Earth's interior, affecting the distribution of elements and the planet's subsequent geological evolution. As the violence of the giant impact subsided and both Earth and Moon began to cool, our planet entered a new phase of its history. The magma ocean that covered Earth's surface began to solidify, forming the first primitive crust. This crust was thin and unstable, constantly being disrupted by volcanic eruptions and impacts from the debris still orbiting in the inner solar system. But it was a beginning, the first solid ground on what would eventually become our world. The atmosphere above this primitive crust was thick and hot, dominated by water vapor and carbon dioxide. As the surface cooled, something remarkable began to happen. The water vapor in the atmosphere began to condense first into clouds, then into rain. This was not gentle rain like we experience today. It was a deluge of almost unimaginable intensity, a global rainstorm that may have lasted for millions of years. The rain that fell on the early Earth was hot, perhaps near the boiling point, and highly acidic from dissolved carbon dioxide. It fell on a surface that was still warm, sometimes pooling in low areas before evaporating back into the atmosphere. But gradually, as the surface continued to cool, more and more water was able to remain liquid. The first oceans began to form, shallow and warm and acidic, but oceans nonetheless. This transition from a molten hellscape to a world with liquid water was one of the most important transformations in Earth's history. Liquid water is essential for life as we know it, and its presence on Earth would eventually make our planet unique among all the worlds we have discovered. But the early oceans were not hospitable by modern standards. They were hot, acidic, and bathed in ultraviolet radiation from the young sun. The atmosphere provided little protection, containing no ozone layer to block harmful rays. And yet within these hostile waters the chemistry of life was already beginning. Simple organic molecules, the building blocks of more complex structures, were forming through various chemical processes. Some may have been delivered by comets and asteroids, which contain significant amounts of organic material. Others may have formed in the atmosphere through reactions driven by lightning or ultraviolet light. Still others may have been synthesized at hydrothermal vents on the ocean floor, where hot, mineral-rich water emerged from volcanic fissures. The stage was being set for the most remarkable transformation of all, the emergence of life. But that story belongs to a later chapter. For now, let yourself rest with the image of the young Earth. No longer a ball of molten rock, but a world with solid ground and liquid water, a world where the conditions for life were slowly coming together. The violence of Earth's birth was fading into the past, replaced by the gentler processes of cooling, condensation, and chemical evolution. Take a deep breath and let your body relax even more deeply. The story of Earth is a long one, and we have only just begun. There is no need to hurry. The planet took billions of years to become what it is today, and we have all the time we need to explore its history. Let the images of the early Earth fade gently from your mind as we prepare to move forward in time, to an era when our planet was still young, but beginning to show the first hints of the world it would become. Section 3. The Hadean Eon. Hell on Earth. The earliest period of Earth's history has been given a fitting name by scientists. They call it the Hadean Eon, after Hades, the Greek god of the underworld. This name evokes images of fire and brimstone, of a hellish landscape utterly unlike the Earth we know today. And indeed, for the first 500 million years or so of our planet's existence, Earth was a world that would seem more at home in a nightmare than in our solar system. The Hadean Eon spans from Earth's formation around 4.5 billion years ago to approximately 4 billion years ago. During this immense stretch of time, Earth transformed from a completely molten ball of rock to a planet with a solid crust, liquid oceans, and the first hints of the conditions necessary for life. It was a time of extremes, of catastrophic violence punctuated by periods of relative calm, of gradual cooling, interrupted by sudden reheating events. Let yourself settle even more comfortably as we explore this ancient and alien time. The Hadean Earth is so different from our modern world that it almost seems like a different planet entirely. And yet everything we see around us today, every mountain and ocean, every living creature, every breath of air, all of it traces its origins back to processes that began during this hellish era. In the immediate aftermath of the moon-forming impact, the Earth was essentially a ball of magma. The entire surface was molten, glowing orange and red, with temperatures exceeding 1,000 degrees Celsius. There was no solid ground anywhere on the planet, just an endless ocean of liquid rock, churning and convecting as heat from the interior made its way to the surface. Above this magma ocean hung a thick atmosphere, nothing like the air we breathe today. This early atmosphere was dominated by rock vapour, silicate gases that had been vaporized by the tremendous heat of the giant impact. Mixed with this rock vapour were water vapour, carbon dioxide, nitrogen, and various sulfur compounds, all outgassed from the molten interior. The atmospheric pressure at the surface may have been hundreds of times greater than today's, creating a crushing, superheated environment. The sky during this time would have been unlike anything we can easily imagine. There was no blue sky, no white clouds, no golden sunshine. Instead, the atmosphere was a thick, opaque shroud of orange and red, illuminated from below by the glow of the magma surface. The sun, if it could be seen at all through the murky atmosphere, would have appeared as a dim, diffuse glow rather than a distinct disk. The newly formed moon, still very close to Earth, would have been visible as a massive presence in the sky, itself glowing with the heat of its own magma ocean. Gradually, over thousands and then millions of years, this hellish world began to cool. The rock vapour in the atmosphere condensed, falling back to the surface as a rain of molten droplets. The magma ocean began to solidify, forming a thin crust of solid rock floating on the still liquid interior. This first crust was probably composed of minerals, similar to those found in modern basalt, dark-coloured rocks, rich in iron and magnesium. But this early crust was unstable and short-lived. The interior of the Earth was still tremendously hot, and convection currents in the underlying magma constantly disrupted the thin solid layer. Volcanic eruptions were frequent and massive, far larger than anything seen on Earth today. These eruptions would have torn through the crust, releasing floods of lava that covered vast areas before cooling and solidifying. Adding to the violence were the continuing impacts from space. Although the era of giant planet-forming collisions was largely over, the inner solar system was still crowded with debris. Asteroids and comets of various sizes continued to rain down on Earth, each impact releasing energy and remelting portions of the surface. The largest of these impacts could have been powerful enough to vaporize the early oceans, if any had formed, and reset the surface to a molten state. Scientists have identified a period called the Late Heavy Bombardment, which occurred roughly 4.1 to 3.8 billion years ago, toward the end of the Hadean and the beginning of the following Archean eon. During this time, the rate of impacts on Earth and other inner solar system bodies increased dramatically. The cause of this bombardment is still debated, but one leading theory suggests that gravitational interactions between the giant outer planets caused their orbits to shift, which in turn destabilized the orbits of countless asteroids and comets, sending them careening into the inner solar system. The evidence for the late heavy bombardment comes primarily from the Moon, whose ancient surface preserves a record of impacts that has long since been erased on the geologically active Earth. The Moon's heavily cratered highlands date from this period, testimony to the violence that both worlds endured. On Earth, the effects would have been even more severe, given our planet's larger size and stronger gravity, which would have attracted more impactors and caused them to strike with greater energy. Despite this ongoing violence, the Hadean Earth was slowly becoming more hospitable. As the planet cooled, water vapour in the atmosphere began to condense. At first, any rain that fell would have evaporated before reaching the surface, which was still too hot to allow liquid water to persist. But eventually, the surface cooled enough that water could begin to accumulate. The formation of Earth's first oceans was a gradual process, probably occurring in fits and starts as the planet cooled, was reheated by impacts, and cooled again. The water that filled these early oceans came from multiple sources. Some was released from the interior through volcanic outgassing, water that had been trapped in minerals and was liberated as those minerals melted. Some was delivered by comets and water-rich asteroids that continued to strike the planet. The relative contributions of these different sources are still debated by scientists. The early oceans were not the blue, life-filled waters we know today. They were probably greenish or brownish in colour, tinted by dissolved iron and other minerals leached from the volcanic rocks that lined their basins. The water was warm, perhaps uncomfortably hot by our standards, heated by the still cooling earth beneath and by the thick greenhouse atmosphere above. These primordial seas were also acidic, saturated with carbon dioxide that had dissolved from the atmosphere, forming carbonic acid that would have stung your skin and burned your eyes. Imagine yourself floating above this ancient world, looking down at a planet that is slowly, painfully transforming itself. The surface is a patchwork of dark volcanic rock and steaming bodies of water. There are no continents as we know them, no familiar shapes of land masses. Instead, countless volcanic islands dot the global ocean, some rising fresh from the depths, others slowly eroding back into the sea. Steam rises constantly from the water's surface, feeding the thick clouds that blanket the sky. The volcanic activity during the Hadean was unlike anything we see on Earth today. The planet's interior was much hotter than it is now, and this heat needed to escape. Volcanoes were the primary mechanism for releasing this internal energy, and they were far more numerous and far more active than modern volcanoes. Some scientists estimate that volcanic activity during the Hadean may have been 10 to 20 times more intense than it is today. These ancient volcanoes were not the graceful cone-shaped mountains we picture when we think of volcanoes today. Many were broad, flat shield volcanoes built up by countless flows of fluid lava spreading across the surface. Others were violent, explosive volcanoes that hurled ash and rock high into the atmosphere. Still others were submarine volcanoes erupting on the ocean floor and building up underwater mountains that sometimes broke the surface to form new islands. The lava that poured from these volcanoes was primarily basalt, a dark iron-rich rock that forms when mantle material melts and rises to the surface. This basaltic crust was denser than the granite-rich continental crust that would form later, and it behaved differently. It was constantly being recycled back into the mantle, pulled down by its own weight and by the convective motions of the underlying rock. The Hadean Earth had no permanent continents, just a constantly shifting mosaic of volcanic islands and ocean floor. As the oceans grew and the crust stabilized, something remarkable began to happen at the boundaries where seawater met hot volcanic rock. Chemical reactions between the water and the rock released minerals and created complex chemical gradients. In some places, hot water laden with dissolved minerals emerged from cracks in the ocean floor, creating hydrothermal vents. These vents, similar to the black smokers and white smokers found on the modern ocean floor, may have been far more common during the Hadean than they are today. The chemistry occurring at these hydrothermal vents was extraordinarily complex. Hot, mineral-rich fluids mixed with cooler seawater, creating steep temperature and chemical gradients. Minerals precipitated out of solution, building up chimney-like structures around the vents. And in this energetic, chemically diverse environment, simple organic molecules began to form and accumulate. Scientists have long been fascinated by the possibility that life originated at hydrothermal vents. These environments provide several key ingredients for the origin of life: a source of energy in the form of chemical gradients, a supply of raw materials in the form of dissolved minerals, and protected niches where complex chemistry can occur without being disrupted. The porous, mineral-rich structures around vents could have served as natural laboratories, concentrating organic molecules and catalyzing reactions that would otherwise occur too slowly to matter. But we are getting ahead of ourselves. Life would not emerge until later in our story. For now, let us remain in the Hadean, appreciating the slow transformation of our world from a hellscape to something approaching habitability. The atmosphere of the Hadean Earth was also evolving. As the surface cooled and oceans formed, much of the water vapour that had dominated the early atmosphere condensed and fell as rain. This left behind an atmosphere composed primarily of carbon dioxide and nitrogen, with smaller amounts of methane, ammonia, and other gases. The atmospheric pressure was still much higher than today's, perhaps 10 to 100 times greater, due to the large amount of carbon dioxide present. This thick carbon dioxide atmosphere created a powerful greenhouse effect, trapping heat and keeping the surface warm, despite the fact that the young sun was actually dimmer than it is today. Scientists call this the faint young sun paradox. Geological evidence suggests that Earth had liquid water throughout most of its history, but calculations show that the sun's output 4 billion years ago was only about 70% of its current value. Without some mechanism to trap additional heat, Earth should have been frozen solid. The greenhouse effect of the early atmosphere provides the solution to this paradox. Carbon dioxide, methane, and water vapour are all greenhouse gases, meaning they allow sunlight to pass through to the surface, but absorb and re-radiate the infrared radiation that the surface emits. With enough of these gases in the atmosphere, Earth could maintain liquid water even under a dimmer sun. The Hadean atmosphere also lacked one component that we take for granted today: free oxygen. The air we breathe is about 21% oxygen, a gas that is essential for complex animal life, but highly reactive and corrosive. During the Hadean, there was essentially no free oxygen in the atmosphere. Any oxygen that was released by geological processes was quickly consumed by reactions with iron and other reduced materials at the surface. This lack of oxygen had important implications for the chemistry of the early Earth. Without oxygen, there was no ozone layer to block ultraviolet radiation from the sun. The surface of the Hadean Earth was bathed in intense UV light, which would be lethal to most modern organisms. However, this same UV radiation may have played a role in the origin of life, providing energy for chemical reactions that could create complex organic molecules. As the Hadean progressed, the rate of impacts from space gradually declined. The inner solar system was slowly being cleared of debris as planets swept up the remaining planetesimals. Each impact that did occur was a setback for the developing Earth, releasing energy, vaporizing portions of the ocean, and disrupting whatever fragile chemical systems might have been developing. But the intervals between major impacts grew longer, allowing more time for the planet to recover and evolve. By about 4.1 billion years ago, Earth had developed a relatively stable crust, global oceans, and a thick atmosphere. The surface was still much hotter than today, and volcanic activity was still intense. but the planet was no longer the completely molten hellscape it had been in the immediate aftermath of its formation. The stage was being set for the next chapter in Earth's history, the Archean Eon, when the first tentative stirrings of life would begin. Let yourself take a moment to appreciate how far Earth had come in its first 500 million years. From a cloud of gas and dust to a growing ball of molten rock to a world with oceans and atmosphere, our planet had undergone transformations that seem almost miraculous. And yet, in a sense, these changes were inevitable, the natural result of physical and chemical processes operating over immense spans of time. The Hadean Earth was not a welcoming place by any standard we would recognize. It was hot, violent, and bathed in deadly radiation. And yet, it was our world, the same planet we live on today, just in an earlier, more turbulent stage of its development. Every atom that made up the Hadean Earth is still here, recycled and rearranged countless times over the billions of years since. But fundamentally, the same matter that condensed from the solar nebula so long ago. As we prepare to leave the Hadean behind and move into the Archean Eon, let your body sink even deeper into relaxation. The violence of Earth's early history is fading now, replaced by gentler processes of cooling, chemical evolution, and the first emergence of life. The story is about to become even more remarkable as simple chemistry gives way to biology, and our planet begins its long journey toward becoming the living world we know today. Section 4, the Archean Eon, First Breath of Life. We now enter the Archean Eon, a vast stretch of time spanning from about 4 billion years ago to 2.5 billion years ago. This period, lasting 1.5 billion years, witnessed some of the most profound transformations in Earth's history. The planet cooled further, the first true continents began to form, and most remarkably of all, life emerged and began to spread across the globe. The name Archean comes from the Greek word for ancient or beginning, and it is a fitting title for this era. Although the Hadean came before it, the Archean is the oldest period from which we have substantial rock records. The violent recycling of the Hadean crust destroyed almost all evidence of that earlier time, but Archean rocks have survived in several locations around the world, providing precious windows into our planet's deep past. As you settle into this next chapter of Earth's story, let the immense timescales wash over you like gentle waves. 1.5 billion years is almost impossible for the human mind to truly grasp. If you were to count one number per second, it would take you about 47 years to count to 1.5 billion. The Archean lasted longer than the time from the extinction of the dinosaurs to the present day, multiplied by 20. It was an era of slow, patient change, of processes operating over millions and hundreds of millions of years to gradually transform our world. The early Archean Earth was still a harsh place by modern standards, but it was significantly calmer than the Hadean had been. The rate of major impacts had declined substantially, though occasional large asteroids and comets still struck the planet. The surface had cooled enough that a stable crust could persist, though it was still much thinner and more active than today's crust. Volcanic activity remained intense, with lava flows and eruptions occurring constantly around the globe. The oceans of the early Archean covered most of the planet's surface, much as they do today. However, the geography was entirely different. There were no large continents, no Atlantic or Pacific, no familiar coastlines. Instead, the ocean was dotted with volcanic islands and small proto-continents, patches of slightly different rock that were beginning to accumulate and resist being recycled back into the mantle. The formation of continents is one of the great stories of the Archean Eon. Continental crust is fundamentally different from oceanic crust. While oceanic crust is composed primarily of dense basalt, continental crust is made largely of granite and related rocks, which are less dense and therefore float higher on the underlying mantle. This buoyancy is what allows continents to persist over billions of years, while oceanic crust is constantly being created and destroyed. The exact mechanism by which the first continental crust formed is still debated by scientists. One possibility is that it formed through the partial melting of basaltic crust that had been pushed down into the mantle, a process similar to what happens at modern subduction zones. As the basalt descended and heated up, the components with lower melting points would liquefy first, creating a magma with a different composition than the original rock. This magma, being less dense than its surroundings, would rise back to the surface and solidify as granitic rock. Whatever the mechanism, by the middle of the Archean, small patches of continental crust had begun to accumulate. These early continents were nothing like the vast land masses we know today. They were small, isolated, and constantly being modified by volcanic activity and erosion. But they represented something new in Earth's history. Land that could persist over long periods, accumulating sediments, and providing stable environments where complex geological and eventually biological processes could occur. The atmosphere of the Archean was still very different from today's. It remained dominated by nitrogen and carbon dioxide, with no free oxygen to speak of. The greenhouse effect of this thick atmosphere kept the planet warm despite the still faint sun. Methane, produced by early microorganisms and by geological processes, may have contributed significantly to this greenhouse warming. The lack of oxygen meant there was still no ozone layer, and the surface remained bathed in intense ultraviolet radiation. This radiation would be lethal to most modern organisms, but it may have been less of a problem for early life, which likely originated in protected environments like deep ocean waters or hydrothermal vents where the UV could not penetrate. And now we come to the most remarkable event of the Archean Eon, indeed one of the most remarkable events in the entire history of the universe, as far as we know, the origin of life. Somewhere on the early Earth, probably during the late Hadean or early Archean, simple chemistry crossed a threshold and became biology. Non-living matter organized itself into self-replicating, evolving systems that we would recognize as alive. The origin of life remains one of the greatest unsolved mysteries in science. We do not know exactly when, where, or how it happened. We do not have fossils of the very first living things, and the chemical traces they might have left have long since been erased by billions of years of geological activity. What we do have are tantalizing clues, theoretical models, and laboratory experiments that suggest possible pathways from chemistry to biology. What we can say with confidence is that life had emerged by about 3.5 billion years ago, and possibly much earlier. The evidence for this comes from several sources. The oldest are chemical signatures in ancient rocks, subtle imbalances in the ratios of carbon isotopes that suggest biological processing. Living organisms preferentially use the lighter isotope of carbon, carbon-12, over the heavier carbon-13, and this preference leaves a distinctive signature in organic matter and in the carbonates formed from it. More dramatic evidence comes from stromatolites, layered rock structures that are formed by communities of microorganisms. The oldest widely accepted stromatolites date from about 3.5 billion years ago, found in the Pilbara region of Western Australia and the Barberton Greenstone Belt of South Africa. These ancient structures look remarkably similar to stromatolites being formed today by cyanobacteria in places like Shark Bay, Australia, suggesting that the organisms that built them were already sophisticated and well established. If life existed 3.5 billion years ago in forms complex enough to build stromatolites, it must have originated even earlier. Some scientists argue that life may have emerged during the late Hadean, only to be wiped out by major impacts, then emerged again, possibly multiple times, before finally gaining a permanent foothold. Others suggest that life originated once and somehow survived the late heavy bombardment, perhaps in deep ocean refuges protected from the worst effects of impacts. Wherever and whenever life originated, the early Archean saw it spread and diversify across the planet. The first living things were almost certainly single-celled organisms, far simpler than any cell alive today. They lacked nuclei, mitochondria, and other complex internal structures. They were what we would now call prokaryotes, similar in basic organization to modern bacteria and archaea. These early organisms faced challenges that modern life does not have to contend with. There was no oxygen for respiration, so they had to obtain energy through other means. Some may have been chemotrophs, deriving energy from chemical reactions involving minerals and dissolved gases. Others may have been early phototrophs, capturing energy from sunlight, though not through the oxygen-producing photosynthesis that would come later. The environment in which these early organisms lived was also challenging. The oceans were warm, perhaps uncomfortably hot by our standards, with temperatures that may have exceeded 50 or even 70 degrees Celsius in some areas. The water was rich in dissolved iron and other metals, giving it a greenish or brownish tint. Hydrothermal vents pumped mineral-laden fluids into the ocean, creating local environments of extreme heat and chemical activity. And yet life thrived. The early prokaryotes found niches where they could survive and reproduce, passing their genetic information to the next generation, with small variations that allowed evolution to occur. Over millions of years, they diversified into countless forms, each adapted to a particular environment or way of life. The tree of life was beginning to branch, though all of its branches were still microscopic and invisible to any hypothetical observer. One of the most important developments of the Archean was the evolution of photosynthesis. The ability to capture energy from sunlight and use it to build organic molecules from carbon dioxide was a revolutionary innovation, freeing organisms from dependence on the limited chemical energy available at hydrothermal vents and other geological features. The first photosynthetic organisms probably used a form of photosynthesis that did not produce oxygen. Instead, they may have used hydrogen sulfide, hydrogen gas, or iron compounds as the electron donors needed to power the photosynthetic reaction. This type of photosynthesis, called anoxygenic photosynthesis, is still used by some bacteria today, particularly those living in environments where oxygen is scarce. But at some point during the Archean, probably around 3 billion years ago, or perhaps earlier, a group of organisms evolved a new and more powerful form of photosynthesis. These were the cyanobacteria, sometimes called blue-green algae, though they are actually bacteria rather than true algae. Cyanobacteria developed the ability to use water as the electron donor for photosynthesis, splitting water molecules and releasing oxygen as a byproduct. This innovation, called oxygenic photosynthesis, would eventually transform the Earth in ways that its inventors could never have anticipated. But for hundreds of millions of years, the oxygen produced by cyanobacteria had little effect on the atmosphere. It was immediately consumed by reactions with dissolved iron in the oceans and with reduced minerals on land. The Earth was like a giant sponge for oxygen, soaking up every molecule that the cyanobacteria produced. The evidence for this comes from banded iron formations, distinctive rock layers found in Archean and early Proterozoic sediments around the world. These formations consist of alternating bands of iron-rich and iron-poor layers, sometimes extending for hundreds of meters in thickness. They formed when dissolved iron in the oceans reacted with oxygen produced by cyanobacteria, precipitating out as iron oxides that settled to the ocean floor. The banded iron formations represent one of the largest ore deposits on Earth, and they are the source of most of the iron ore mined today. They also represent a record of the slow oxygenation of Earth's environment, as generation after generation of cyanobacteria pumped oxygen into the oceans only to have it consumed by the vast reservoir of dissolved iron. As the Archean progressed, the continents continued to grow. By the end of the eon, around 2.5 billion years ago, there may have been enough continental crust to form one or more small supercontinents. These early land masses were probably clustered near the equator, where the climate was warmest, though they were constantly being rearranged by the motions of plate tectonics. The growth of continents had important implications for Earth's climate and chemistry. Continental rocks weather more easily than oceanic basalt, and this weathering draws carbon dioxide out of the atmosphere. As more continental crust accumulated, more carbon dioxide was removed from the air, potentially cooling the climate. At the same time, the nutrients released by weathering washed into the oceans, fertilizing the growth of photosynthetic organisms. The Archean was also a time of intense geological activity beyond just volcanism. The Earth's interior was hotter than it is today, and this heat drove vigorous convection in the mantle. Plate tectonics may have operated differently than it does now, with smaller, faster-moving plates and more frequent volcanic eruptions. Some scientists have proposed that the early Earth had a different tectonic style altogether, with a more mobile, less rigid crust that behaved almost like a thick liquid. Throughout all of this geological activity, life persisted and spread. By the end of the Archean, microorganisms had colonized virtually every environment on Earth where liquid water existed. They lived in the open ocean, in shallow coastal waters, in hot springs, in the pores of rocks, and perhaps even on the surfaces of the early continents. They had developed a remarkable diversity of metabolic strategies, finding ways to extract energy from sunlight, from chemical reactions, and from organic matter produced by other organisms. The Archean Earth was not a beautiful world by human standards. There were no forests, no flowers, no animals, no birdsong. The land was barren rock, the sea was greenish-brown, and the sky was hazy with volcanic emissions. And yet it was a living world, the first living world in our solar system, as far as we know. The spark of life that had ignited during this eon would never be extinguished. It would grow, diversify, and eventually transform the planet in ways that the first simple cells could never have imagined. As we prepare to leave the Archean behind, take a moment to appreciate the profound significance of what happened during this time. Life emerged from non-life, a transition that may be common in the universe or may be vanishingly rare. We do not yet know which is the case, but we do know that it happened here on our world, in the warm and turbulent oceans of the Archean Earth. Everything that followed, every plant and animal, every ecosystem and civilization, all of it traces back to those first simple cells dividing in the ancient sea. Let your breathing slow and your body relax as we move forward in time, into the Proterozoic eon, when life would begin to transform the Earth in dramatic and visible ways. The story is far from over. In many ways, it is just beginning. Section 5, the Proterozoic Eon, the Oxygen Revolution and Snowball Earth. We now enter the Proterozoic Eon, an immense span of time stretching from 2.5 billion years ago to just 538 million years ago. This eon, lasting nearly 2 billion years, is the longest formally defined unit of geological time, and it witnessed some of the most dramatic transformations in Earth's history. During the Proterozoic, the atmosphere was fundamentally altered. The planet froze over multiple times, and life evolved from simple single cells to complex multicellular organisms. The name Proterozoic means earlier life, a reference to the fact that this eon preceded the explosion of complex animal life that would characterize the following Phanerozoic eon. But the name is somewhat misleading because the Proterozoic was far from lifeless. It was during this time that life began to truly reshape the planet, transforming the chemistry of the atmosphere and oceans in ways that would make complex life possible. As you settle into this next chapter of our journey, let the vast timescales continue to wash over you. 2 billion years is an almost incomprehensible length of time. If the entire history of the Earth were compressed into a single year, the Proterozoic would span from mid-March to mid-November, more than 8 months of our planetary calendar. So much happened during this time, and yet so much of it happened so slowly that it would have been imperceptible to any observer. The most significant event of the early Proterozoic was the Great Oxidation Event, sometimes called the Oxygen Catastrophe or the Oxygen Revolution. This was the moment when free oxygen finally began to accumulate in Earth's atmosphere, fundamentally changing the chemistry of our planet and setting the stage for all complex life that would follow. For hundreds of millions of years during the Archean, cyanobacteria had been producing oxygen through photosynthesis, but this oxygen had been immediately consumed by reactions with dissolved iron in the oceans and with reduced minerals on land. The Earth had an enormous oxygen debt, a vast reservoir of materials that could react with oxygen, and this debt had to be paid before oxygen could begin to accumulate in the atmosphere. By about 2.4 billion years ago, the debt was finally paid. The dissolved iron in the oceans had largely been precipitated out as banded iron formations. The reduced minerals on land had been oxidized, and suddenly there was nowhere for the oxygen to go except into the atmosphere. The concentration of atmospheric oxygen began to rise, slowly at first, then more rapidly, until it reached levels that would have been toxic to most of the organisms that had evolved in the previous oxygen-free world. The Great Oxidation Event was a catastrophe for the anaerobic organisms that had dominated the Earth for over 1 billion years. Oxygen is a highly reactive gas, and for organisms that had evolved in its absence, it was a deadly poison. The rise of oxygen must have caused a mass extinction of anaerobic life, driving these organisms into the shrinking refuges where oxygen could not penetrate: deep sediments, oxygen-poor waters, and the interiors of other organisms. But for other organisms, the rise of oxygen was an opportunity. Oxygen is a powerful oxidizing agent, and reactions involving oxygen release far more energy than the anaerobic reactions that had powered life up to this point. Organisms that could tolerate oxygen, and eventually those that could use it for respiration, had access to a much richer energy source than their anaerobic ancestors. The rise of oxygen also had profound effects on Earth's climate. Methane, which had been an important greenhouse gas during the Archean, reacts with oxygen and is destroyed. As oxygen levels rose, methane levels fell, reducing the greenhouse effect and cooling the planet. At the same time, the oxidation of reduced minerals on land may have drawn carbon dioxide out of the atmosphere, further reducing the greenhouse effect. The result was the first great ice age in Earth's recorded history, a series of glaciations known collectively as the Huronian glaciation, occurring between about 2.4 and 2.1 billion years ago. During these glaciations, ice sheets spread from the poles toward the equator, covering large portions of the continents and chilling the oceans. The extent of these early ice ages is difficult to determine from the fragmentary geological record, but they appear to have been severe, possibly covering much of the planet in ice. The Huronian glaciation eventually ended, probably as volcanic activity continued to pump carbon dioxide into the atmosphere, rebuilding the greenhouse effect. The planet warmed, the ice retreated, and life continued to evolve. But this first great ice age was a harbinger of things to come. The Proterozoic would see even more severe glaciations, events so extreme that scientists have given them a dramatic name: Snowball Earth. Before we explore the Snowball Earth events, let us consider what was happening with life during the Middle Proterozoic, the long stretch of time between about 2.1 billion and 800 million years ago. This period is sometimes called the Boring Billion because the geological and biological record seems relatively uneventful compared to what came before and after. But this apparent monotony masks important developments that were setting the stage for the explosion of complex life that would follow. During the Boring Billion, atmospheric oxygen levels remained relatively low, probably between 1 and 10% of present levels. This was enough to support aerobic respiration, but not enough to allow the development of large, active animals. The oceans were stratified, with oxygenated surface waters overlying deeper waters that remained oxygen-poor or completely anoxic. Life was dominated by single-celled organisms, both prokaryotes and the newly evolved eukaryotes. The evolution of eukaryotes was one of the most important developments of the Proterozoic. Eukaryotic cells are fundamentally different from prokaryotic cells like bacteria. They are larger, more complex, and contain membrane-bound organelles, including a nucleus that houses their DNA. The origin of eukaryotes appears to have involved a remarkable event called endosymbiosis, in which one prokaryotic cell engulfed another without digesting it, and the two formed a permanent partnership. The most important of these endosymbiotic events was the acquisition of mitochondria, the organelles that carry out aerobic respiration in modern eukaryotic cells. Mitochondria are descended from free-living bacteria that were engulfed by an ancestral eukaryotic cell sometime during the Proterozoic. The engulfed bacteria provided their host with the ability to efficiently extract energy from organic molecules using oxygen, while the host provided protection and a steady supply of nutrients. A similar event led to the origin of chloroplasts, the organelles that carry out photosynthesis in plants and algae. Chloroplasts are descended from cyanobacteria that were engulfed by eukaryotic cells, probably on multiple independent occasions. This endosymbiotic origin explains why chloroplasts, like mitochondria, have their own DNA and reproduce by division, independently of the cell that contains them. The evolution of eukaryotes opened up new possibilities for life. Eukaryotic cells are capable of becoming much larger than prokaryotic cells because their internal membrane systems allow for more efficient transport of materials within the cell. They are also capable of more complex behaviors, including the ability to engulf and digest other cells, a process called phagocytosis that is impossible for prokaryotes. Perhaps most importantly, eukaryotic cells are capable of forming true multicellular organisms, in which different cells take on specialized roles and cooperate to form a functioning whole. While some prokaryotes form colonies and biofilms, they do not achieve the level of cellular differentiation and integration seen in multicellular eukaryotes. The evolution of eukaryotes was therefore a prerequisite for the evolution of plants, animals, fungi, and all other complex multicellular life. The first multicellular eukaryotes appear in the fossil record during the Middle to Late Proterozoic. The oldest widely accepted fossils of multicellular organisms are filamentous algae and seaweeds, dating from about 1.2 billion years ago. These early multicellular organisms were relatively simple, consisting of chains or sheets of similar cells without much specialization. But they represented a new level of biological organization, a step toward the complex body plans that would characterize later life. Now let us turn to the dramatic climatic events of the late Proterozoic, the Snowball Earth glaciations that occurred between about 720 and 635 million years ago. These were among the most severe ice ages in Earth's history. events so extreme that they may have covered the entire planet in ice from pole to pole, including the tropical oceans. The evidence for snowball Earth comes from glacial deposits found on every continent, including some that were located at tropical latitudes during the late Proterozoic. These deposits include distinctive rock types called diamictites, unsorted mixtures of boulders, pebbles, sand and clay that are characteristic of glacial environments. The presence of such deposits near the ancient equator suggests that ice sheets extended all the way from the poles to the tropics, something that has not happened at any other time in Earth's history. The cause of the snowball Earth events is still debated, but several factors probably contributed. The breakup of the supercontinent Rodinia, which occurred during this time, may have altered ocean circulation patterns and increased weathering rates, drawing carbon dioxide out of the atmosphere. The weathering of newly exposed rock surfaces would have consumed carbon dioxide, reducing the greenhouse effect and cooling the planet. Once ice began to spread, a powerful feedback mechanism came into play. Ice is highly reflective, bouncing sunlight back into space rather than absorbing it. As ice sheets expanded, they reflected more and more sunlight, cooling the planet further and allowing the ice to expand even more. This ice albedo feedback can create a runaway glaciation, potentially covering the entire planet in ice. A fully frozen Earth would have been a strange and hostile world. The oceans would have been covered by ice perhaps a kilometre thick, blocking sunlight from reaching the water below. Photosynthesis would have essentially ceased in the oceans, though some may have continued in meltwater pools, on the ice surface, or in rare patches of open water. The land would have been buried under massive ice sheets, scoured clean of soil and life. And yet life survived. We know this because we are here, and because the fossil record shows continuity across the snowball Earth events. How life persisted through these global glaciations is not entirely clear, but several refugia have been proposed. Hydrothermal vents on the ocean floor would have continued to provide warmth and chemical energy, supporting communities of organisms independent of sunlight. Geothermal hot springs on land may have created small oases of liquid water, and some organisms may have survived in the ice itself, in tiny pockets of liquid water, or in the thin films of water that exist at grain boundaries within ice. The snowball Earth events ended dramatically. Volcanic activity continued throughout the glaciations, pumping carbon dioxide into the atmosphere. Normally, this carbon dioxide would be removed by weathering of rocks and absorption by the oceans, but with the continents buried under ice and the oceans frozen over, these removal mechanisms were shut down. Carbon dioxide accumulated in the atmosphere, eventually reaching concentrations perhaps hundreds of times higher than today's levels. At some point, the greenhouse effect of this accumulated carbon dioxide became strong enough to overcome the reflective cooling of the ice. The ice began to melt, first at the equator where sunlight was most intense, then spreading toward the poles. The transition from icehouse to greenhouse was probably rapid by geological standards, perhaps occurring over just a few thousand years. The Earth swung from one extreme to another, from a frozen snowball to a sweltering hothouse. The aftermath of the snowball Earth events saw dramatic changes in Earth's environment and life. Weathering of the newly exposed continents released nutrients into the oceans, fertilizing a bloom of photosynthetic organisms. Oxygen levels in the atmosphere rose significantly, possibly reaching levels close to those of today for the first time. And in this newly oxygenated world, complex multicellular life began to flourish as never before. The period immediately following the last snowball Earth event, from about 635 to 538 million years ago, is called the Ediacaran period. It is named after the Ediacara Hills in South Australia, where fossils of strange soft-bodied organisms were first discovered in the 1940s. These Ediacaran organisms represent the first large, complex, multicellular life in the fossil record, and they remain mysterious and enigmatic to this day. The Ediacaran biota included a bizarre menagerie of organisms unlike anything alive today. There were frond-like forms that may have been related to modern sea pens, or may have been something entirely different. There were disc-shaped organisms that may have been jellyfish-like creatures, or may have been something else entirely. There were segmented, worm-like forms, and strange quilted organisms that have no clear modern analogues. Scientists debate the relationships of the Ediacaran organisms to modern life. Some may have been early animals, ancestors or relatives of the creatures that would dominate the following era. Others may have been members of entirely extinct kingdoms of life, evolutionary experiments that ultimately left no descendants. The Ediacaran world was a strange one, populated by creatures that seem almost alien to our modern eyes. What is clear is that the Ediacaran period was a time of biological innovation and experimentation. For the first time, organisms grew to sizes visible to the naked eye, some reaching lengths of over a metre. For the first time, organisms developed complex body plans with differentiated tissues and organs. For the first time, organisms began to interact with each other and with their environment in complex ways, moving through the water, burrowing into sediments, and perhaps even preying upon one another. The Ediacaran world was a quiet one compared to what would come later. There were no shells, no skeletons, no hard parts of any kind. The organisms were soft-bodied, leaving fossils only under exceptional circumstances when they were rapidly buried in fine sediment. There were no eyes that we can detect, no jaws, no claws. If you could somehow travel back to an Ediacaran seafloor, you might find it peaceful, even serene, a garden of strange, gently waving fronds and slowly creeping forms. The seafloors of the Ediacaran were often covered with thick mats of microorganisms, similar to the stromatolite building communities that had existed since the Archean. These microbial mats provided food for some Ediacaran organisms and substrate for others. The relationship between the large Ediacaran organisms and the microbial mats that carpeted their world was probably complex, with some organisms grazing on the mats, others living within them, and still others simply resting upon them. One of the most intriguing aspects of the Ediacaran biota is how suddenly it disappeared. At the end of the Ediacaran period, around 538 million years ago, most of these strange organisms vanished from the fossil record. They were replaced by an entirely new cast of characters, the animals of the Cambrian period, which bore little obvious resemblance to their Ediacaran predecessors. Whether this transition was gradual or abrupt, whether it involved mass extinction or simply ecological replacement, remains a subject of active research and debate. As we prepare to leave the Proterozoic eon behind, let us take a moment to appreciate the immense changes that occurred during this 2 billion year span. The atmosphere was transformed from an oxygen-free mixture of nitrogen and carbon dioxide to something approaching the oxygen-rich air we breathe today. The planet experienced the most severe glaciations in its history, freezing over completely at least twice. Life evolved from simple single cells to complex multicellular organisms with differentiated tissues and organs. The stage was set for the explosion of animal life that would characterize the following era. The Proterozoic was a time of preparation, of slow accumulation of the conditions necessary for complex life. The oxygen that accumulated in the atmosphere would power the active metabolisms of animals. The nutrients released by weathering would fertilize the oceans. The evolution of eukaryotes and multicellularity would provide the cellular toolkit for building complex bodies. Everything was coming together, converging toward a moment of biological revolution that would transform the Earth forever. Let your body relax even more deeply as we move forward in time, crossing the boundary from the Proterozoic to the Phanerozoic eon, from the world of microscopic life and soft-bodied enigmas to the world of animals with shells and skeletons, eyes and teeth, predators and prey. The story of Earth is about to accelerate as life begins to evolve at a pace never seen before. Section 6. The Cambrian Explosion and the Paleozoic Era. We now enter the Phanerozoic eon, the eon of visible life, which began 538 million years ago and continues to the present day. The Phanerozoic is divided into three eras: the Paleozoic, meaning ancient life, the Mesozoic, meaning middle life, and the Cenozoic, meaning recent life. In this section, we will explore the Paleozoic era, a span of nearly 300 million years, during which life diversified explosively, colonized the land, and experienced some of the most devastating mass extinctions in Earth's history. The Paleozoic era began with one of the most remarkable events in the history of life, the Cambrian explosion. In a geologically brief span of time, perhaps only 20 to 25 million years, the major groups of animals that exist today appeared in the fossil record for the first time. This sudden proliferation of animal life has puzzled and fascinated scientists since it was first recognized in the 19th century, and it remains one of the most intensively studied events in paleontology. Before the Cambrian explosion, the fossil record is dominated by single-celled organisms and the enigmatic soft-bodied creatures of the Ediacaran. After the Cambrian explosion, we find a world teeming with animals possessing hard shells, external skeletons, compound eyes, jointed legs, and a bewildering variety of body plans. The contrast is so stark that early geologists, who did not know about the Ediacaran biota, believed that life had appeared suddenly and fully formed at the beginning of the Cambrian. The Cambrian explosion was not literally an explosion, of course. It unfolded over millions of years, which is a long time by human standards, but remarkably brief by geological standards. The causes of this rapid diversification are still debated, but several factors probably contributed. Rising oxygen levels may have finally reached the threshold necessary to support large active animals. The evolution of predation may have triggered an evolutionary arms race, driving the development of shells, spines, and other defensive structures. The evolution of eyes may have transformed ecological relationships, allowing predators to hunt more effectively and prey to detect and avoid them. The best window into the Cambrian world comes from exceptional fossil deposits called Lagerstätten, where conditions allowed the preservation of soft tissues that normally decay without a trace. The most famous of these is the Burgess Shale in British Columbia, Canada, discovered in 1909 and studied intensively ever since. The Burgess Shale preserves a remarkable snapshot of marine life from about 508 million years ago, including many soft-bodied organisms that would otherwise be completely unknown. The creatures of the Burgess Shale seem almost alien to modern eyes. There is a Nomalocaris, a metre-long predator with large compound eyes grasping appendages near its mouth, and a body that undulated through the water like a living wing. There is Opabinia, a smaller creature with 5 eyes on stalks and a long, flexible proboscis tipped with grasping spines. There is Hallucigenia, a worm-like animal walking on stilt-like legs with long spines projecting from its back. And there are dozens of others, each stranger than the last. Among the Cambrian fauna were the ancestors of all the major animal groups alive today. Primitive chordates, the group that includes vertebrates like ourselves, are represented by small fish-like creatures such as Picaia and Hyquicthys. Arthropods, the group that includes insects, spiders, and crustaceans, were already diverse and abundant, represented most famously by the trilobites. Mollusks, echinoderms, worms of various kinds, and many other groups all made their first appearances during this remarkable period. The trilobites deserve special mention, for they would become one of the most successful and iconic groups of the Paleozoic era. These marine arthropods had bodies divided into 3 lobes, hence their name, and they possessed some of the first sophisticated eyes in the animal kingdom. Trilobite eyes were made of calcite crystals, the same mineral that forms limestone, and some species had hundreds or even thousands of individual lenses, giving them nearly panoramic vision. Trilobites diversified rapidly during the Cambrian and Ordovician periods, filling ecological roles from bottom-dwelling scavengers to swimming predators to burrowing filter feeders. They ranged in size from a few millimeters to over half a meter in length. Their hard exoskeletons fossilized readily, making them among the most common fossils found in Paleozoic rocks. For over 250 million years, trilobites were a dominant presence in the world's oceans, before finally succumbing to the Great Extinction at the end of the Permian period. The Ordovician period, which followed the Cambrian from about 485 to 443 million years ago, saw continued diversification of marine life. This period is sometimes called the Ordovician radiation, or the Great Ordovician biodiversification event, as the number of marine families roughly tripled during this time. The oceans teemed with life, corals built the first great reef systems, cephalopods evolved into formidable predators, and fish began their long evolutionary journey toward dominance of the vertebrate world. The continents during the Ordovician were arranged very differently than they are today. Most of the major land masses were clustered in the southern hemisphere, with a large supercontinent called Gondwana straddling the South Pole. The northern hemisphere was mostly ocean, dotted with smaller continental fragments and volcanic island arcs. Sea levels were high, and shallow seas flooded large portions of the continents, creating vast expanses of warm, sunlit water ideal for marine life. The Ordovician ended with one of the 5 great mass extinctions in Earth's history. Around 443 million years ago, a severe ice age gripped the planet as Gondwana drifted over the South Pole and accumulated massive ice sheets. Sea levels dropped dramatically as water was locked up in glaciers, draining the shallow seas where most marine life lived. The cold temperatures and loss of habitat proved devastating, and an estimated 85% of marine species went extinct. The Silurian period, lasting from about 443 to 419 million years ago, saw life recover from this extinction and continue to diversify. The Ice Age ended relatively quickly, and sea levels rose again, reflooding the continental shelves. Coral reefs, which had been devastated by the extinction, rebuilt and expanded. Fish continued to evolve, with the first jawed fish appearing during this period, an innovation that would prove enormously successful. But perhaps the most significant development of the Silurian was the colonization of land by plants. For the first 4 billion years of Earth's history, the continents had been essentially barren, home only to microbial mats and crusts in moist areas. The land surface was a desert of bare rock, sand and gravel, scoured by wind and rain, with no vegetation to hold the soil in place. The first land plants were small, simple organisms, probably similar to modern mosses and liverworts. They lacked true roots, stems and leaves, and they were confined to moist environments near water. But they represented a revolutionary expansion of life into a new realm, one that would eventually transform the Earth's surface and atmosphere. The challenges of life on land were formidable. Plants needed to support themselves against gravity without the buoyancy of water. They needed to prevent desiccation in the dry air. They needed to transport water and nutrients throughout their bodies without the surrounding medium of water to help. And they needed to reproduce without the water that aquatic plants use to transport their gametes. Over millions of years, plants evolved solutions to all of these challenges. They developed rigid cell walls and supportive tissues to hold themselves upright. They developed waxy coatings and stomata to regulate water loss. They developed vascular systems to transport water and nutrients. And they developed pollen and seeds to reproduce without free water. Each of these innovations opened new possibilities, allowing plants to grow taller, spread into drier environments, and eventually cover the continents in green. The Devonian period, lasting from about 419 to 359 million years ago, is sometimes called the Age of Fishes, for it was during this time that fish reached their greatest diversity and ecological dominance. The oceans were ruled by a variety of fish groups, from the heavily armoured placoderms to the first sharks to the lobe-finned fish that would eventually give rise to land vertebrates. The largest predator of the Devonian seas was Dunkleosteus, a placoderm that could reach lengths of 6 metres or more. Dunkleosteus had no teeth in the conventional sense, but its jaws were lined with sharp, bony plates that could slice through almost anything. Biomechanical studies suggest that Dunkleosteus had one of the most powerful bites of any animal that has ever lived, capable of generating forces comparable to those of large crocodiles or Tyrannosaurus rex. But the most significant evolutionary development of the Devonian was happening not in the open ocean, but in shallow, swampy waters near the shore. Here, a group of lobe-finned fish was evolving the adaptations that would allow their descendants to walk on land. These fish had fleshy, muscular fins supported by bones homologous to the limb bones of land vertebrates. They could use these fins to prop themselves up on the bottom and perhaps to move short distances over land between bodies of water. The transition from fish to land-dwelling tetrapods was a gradual process, occurring over millions of years and involving many intermediate forms. Fossils like Tiktaalik, discovered in the Canadian Arctic in 2004, show animals that were intermediate between fish and tetrapods, with fish-like scales and gills, but also with wrist bones and a neck that allowed the head to move independently of the body. These transitional forms provide compelling evidence for the evolutionary connection between fish and land vertebrates. By the end of the Devonian, the first true tetrapods had emerged, 4-legged vertebrates capable of walking on land. These early tetrapods were not yet fully terrestrial. They probably spent most of their time in water and came onto land only occasionally, but they had taken the crucial first steps in a journey that would eventually lead to dinosaurs, birds, mammals, and humans. The Devonian also saw the continued expansion of plant life on land. Forests appeared for the first time as plants evolved the ability to produce wood and grow to tree-like sizes. The first forests were dominated by plants quite different from modern trees, including giant club mosses and horsetails that could reach heights of 30 metres or more. These forests transformed the landscape, stabilising soils, altering the water cycle, and providing new habitats for the animals that were beginning to colonise the land. The spread of forests had profound effects on Earth's atmosphere and climate. Trees draw carbon dioxide out of the atmosphere through photosynthesis and lock it away in their wood. When the first forests spread across the continents, they removed so much carbon dioxide that the greenhouse effect weakened significantly and global temperatures dropped. The late Devonian saw a series of extinction events, possibly related to this cooling, that eliminated many marine species and set the stage for the next chapter of life's history, the Carboniferous period. Lasting from about 359 to 299 million years ago, takes its name from the vast deposits of coal that formed during this time. Coal is fossilized plant material, the remains of ancient forests that were buried before they could fully decay. The Carboniferous forests were unlike anything that exists today, dominated by giant club mosses, horsetails, and tree ferns that created dense, swampy jungles across much of the tropical regions. The atmosphere during the Carboniferous was very different from today's. Oxygen levels were much higher, perhaps reaching 35% compared to today's 21%. This oxygen-rich air had important consequences for life. Insects, which breathe through a system of tubes called tracheae that limits their maximum size, were able to grow much larger than they can today. The Carboniferous saw giant dragonflies with wingspans of over 70 centimetres and millipedes more than 2 metres long. The high oxygen levels also made the world more flammable. Forest fires were probably common during the Carboniferous, sweeping through the dense vegetation and leaving behind layers of charcoal that we find preserved in the rock record. These fires may have played an important role in the carbon cycle, preventing the complete burial of organic matter and returning some carbon to the atmosphere. The tetrapods that had emerged during the Devonian diversified during the Carboniferous, splitting into two major lineages. One lineage, the amphibians, remained tied to water for reproduction, laying their eggs in ponds and streams as modern frogs and salamanders do. The other lineage evolved a revolutionary innovation, the amniotic egg, a self-contained life support system that allowed reproduction on dry land. The amniotic egg is surrounded by membranes that protect the developing embryo, provide it with nutrients, and allow gas exchange while preventing desiccation. This innovation freed vertebrates from their dependence on water for reproduction, allowing them to colonize drier environments far from ponds and streams. The animals that evolved the amniotic egg are called amniotes, and they include two major groups: the synapsids, which would eventually give rise to mammals, and the sauropsids, which would give rise to reptiles, dinosaurs, and birds. By the end of the Carboniferous, the continents were coming together to form a single supercontinent called Pangaea, meaning all lands. This assembly of continents had profound effects on climate and life. The interior of Pangaea became increasingly arid, as moisture from the oceans could not penetrate far inland. The coal-forming swamps that had characterized the Carboniferous began to shrink, replaced by drier habitats more favorable to amniotes than to amphibians. The Permian period, the final period of the Paleozoic era, lasted from about 299 to 252 million years ago. During the Permian, the assembly of Pangaea was completed, and the world took on a very different character. The tropical swamps of the Carboniferous gave way to vast deserts in the continental interior, while the coasts and polar regions experienced more extreme seasonal variations than ever before. Life adapted to these new conditions. The synapsids, the lineage that would eventually produce mammals, became the dominant land vertebrates during the Permian. Some synapsids evolved to large sizes, becoming the top predators of their ecosystems. Others became herbivores, developing specialized teeth for processing plant material. The diversity of synapsids during the Permian foreshadowed the diversity of mammals that would emerge much later, after the age of dinosaurs. The Permian also saw the continued evolution of plants adapted to drier conditions. Conifers, which had first appeared during the Carboniferous, became increasingly common. These trees were better adapted to drought than the swamp-loving club mosses and horsetails, and they would eventually come to dominate the world's forests. But the Permian is best known for how it ended, with the most devastating mass extinction in Earth's history. The Permian Triassic extinction event, sometimes called the Great Dying, occurred around 252 million years ago and eliminated an estimated 90 to 96% of all marine species and about 70% of terrestrial vertebrate species. It was the closest life has ever come to being completely wiped out. The cause of the Permian extinction was almost certainly volcanic activity on a massive scale. In what is now Siberia, enormous eruptions poured out millions of cubic kilometers of lava, creating a vast volcanic province called the Siberian traps. These eruptions released enormous quantities of carbon dioxide, methane, and sulfur dioxide into the atmosphere, triggering a cascade of environmental changes. The greenhouse gases released by the Siberian traps caused rapid and severe global warming. Temperatures rose by perhaps 10 degrees Celsius or more, making the tropics uninhabitably hot and disrupting ecosystems worldwide. The warming also affected the oceans, reducing the amount of oxygen that could dissolve in seawater and creating vast dead zones where marine life could not survive. The sulfur dioxide released by the eruptions may have caused acid rain, damaging vegetation on land and acidifying the surface waters of the ocean. The combination of warming, ocean anoxia, and acidification proved devastating to marine life. Coral reefs, which had been major features of the marine environment since the Ordovician, were essentially wiped out. Trilobites, which had survived for over 250 million years, finally went extinct. Entire groups of marine organisms disappeared forever. On land, the extinction was also severe, though perhaps not quite as complete as in the oceans. The synapsid-dominated ecosystems of the Permian collapsed, and many lineages went extinct. The survivors faced a devastated world, with reduced vegetation, unstable climates, and empty ecological niches waiting to be filled. The Permian extinction marks the end of the Paleozoic era, the era of ancient life. When life recovered from this catastrophe, it would take on a very different character. The synapsids, which had been the dominant land vertebrates, would be replaced by a new group, the archosaurs, which would give rise to crocodiles, pterosaurs, dinosaurs, and eventually birds. The Mesozoic era, the era of middle life, was about to begin. As we prepare to leave the Paleozoic behind, let your mind dwell for a moment on the immense span of time we have covered. Nearly 300 million years, during which life exploded in diversity, colonized the land, developed forests and complex ecosystems, and then was nearly annihilated by volcanic catastrophe. The Paleozoic saw the evolution of fish, amphibians, and the first reptiles and mammal ancestors. It saw the first plants on land grow into towering forests. It saw the rise and fall of the trilobites, those iconic arthropods that dominated the seas for so long. And yet, despite all the changes and all the extinctions, life persisted. The spark that had been kindled in the Archean oceans billions of years before continued to burn. From the ashes of the Permian catastrophe, new forms of life would emerge, including the most famous inhabitants of Earth's past, the dinosaurs. Let your breathing slow and your body relax as we move forward in time, into the Mesozoic era, the age of dinosaurs. The story continues, and there is still so much to discover. Section 7. The Mesozoic era, the age of dinosaurs. We now enter the Mesozoic era, one of the most celebrated chapters in Earth's long history. Spanning from 252 million years ago to 66 million years ago, the Mesozoic is divided into three periods: the Triassic, the Jurassic, and the Cretaceous. This era witnessed the rise and reign of the dinosaurs, the evolution of the first birds and flowering plants, and the continued drift of continents toward their modern positions. It ended with another mass extinction, one that cleared the stage for the rise of mammals and eventually for us. The Mesozoic began in the aftermath of the Permian extinction, with a world that was devastated and largely empty. The lush forests of the Carboniferous and Permian had been replaced by sparse vegetation struggling to recover. The diverse communities of marine and terrestrial life had been reduced to a handful of survivors. It was a world of opportunity, with countless ecological niches waiting to be filled by whatever organisms could adapt and diversify fastest. The Triassic period, lasting from about 252 to 201 million years ago, was a time of recovery and transition. the survivors of the Permian extinction began to diversify, filling the empty niches left by the vanished species. On land, the archosaurs, a group of reptiles that had been relatively minor players during the Permian, began their rise to dominance. The archosaurs split into two major lineages during the Triassic. One lineage, the crocodile line archosaurs or pseudotsuchians, became the dominant land predators of the early Triassic. These were not the crocodiles we know today, but a diverse array of forms, including large, fully terrestrial predators that walked on upright legs. Some pseudotsuchians were armoured like tanks, while others were swift runners capable of chasing down prey. The other lineage, the birdline archosaurs or Avomete tarsalians, initially played a more modest role, but this lineage would prove to be enormously successful in the long run, for it included the dinosaurs and their flying relatives, the pterosaurs. The first dinosaurs appeared during the Middle Triassic, around 230 to 240 million years ago. They were small, bipedal creatures, probably no larger than a dog, and they were just one of many groups of archosaurs competing for ecological space. The earliest dinosaurs were probably omnivores or carnivores, agile hunters that used their speed and sharp teeth to catch prey. Fossils from Argentina and Brazil have revealed some of these early dinosaurs, including Eoraptor and Herrerasaurus, which show the basic body plan that would characterize the group for the next 165 million years. An upright stance with legs positioned directly beneath the body, a long tail for balance, and grasping hands with sharp claws. The Triassic world was still dominated by the supercontinent Pangaea, though it had begun to show the first signs of breaking apart. The climate was generally warm and dry, with vast deserts covering much of the continental interior. The poles were free of ice and sea levels were relatively low. The vegetation was dominated by conifers, cycads, ginkgos, and ferns, with no flowering plants yet in existence. The end of the Triassic was marked by another mass extinction, though not as severe as the one that had ended the Permian. Around 201 million years ago, volcanic activity associated with the initial breakup of Pangaea triggered environmental changes that eliminated many species. The crocodile line archosaurs, which had been the dominant land animals, were hit particularly hard. The dinosaurs, for reasons that are not entirely clear, fared much better. The Triassic-Jurassic extinction cleared the way for the dinosaurs to become the dominant land animals, a position they would hold for the next 135 million years. The Jurassic period, lasting from about 201 to 145 million years ago, saw the dinosaurs diversify into a bewildering array of forms, from tiny feathered creatures to the largest animals ever to walk the earth. The Jurassic is perhaps best known for the giant sauropod dinosaurs, the long-necked herbivores that are among the most iconic of all prehistoric animals. Sauropods like Brachiosaurus, Diplodocus, and Apatosaurus reached lengths of 25 meters or more and weights of tens of thousands of kilograms. They were the largest land animals that have ever existed, and their sheer size remains a source of wonder and scientific inquiry. How did sauropods grow so large? Several factors probably contributed. Their long necks allowed them to reach vegetation that other herbivores could not access, giving them a competitive advantage. Their relatively small heads and simple teeth suggest they did not chew their food extensively, instead swallowing plant material whole and letting their enormous digestive systems break it down. Their hollow, air-filled bones, similar to those of modern birds, reduced their weight while maintaining structural strength. The predators of the Jurassic were equally impressive. Allosaurus, a large theropod dinosaur reaching lengths of 10 to 12 meters, was one of the top predators of the late Jurassic. Theropods were bipedal carnivores, walking on their powerful hind legs, while their smaller forelimbs were used for grasping prey. They were the ancestors of birds, and many of them were probably covered in feathers, though the largest species may have been mostly or entirely scaly. The Jurassic also saw the evolution of the first birds. The most famous early bird is Archaeopteryx, known from several beautifully preserved fossils found in the limestone quarries of Bavaria, Germany. Archaeopteryx had feathered wings capable of flight, but it also retained many dinosaurian features, including teeth, clawed fingers on its wings, and a long bony tail. It is a perfect transitional form, showing how the features of modern birds evolved gradually from their dinosaurian ancestors. The skies of the Jurassic were also home to the pterosaurs, flying reptiles that were not dinosaurs but were closely related to them. Pterosaurs had evolved flight independently of birds, using wings formed by a membrane of skin stretched between an enormously elongated fourth finger and the body. Some Jurassic pterosaurs were small, no larger than sparrows, while others had wingspans of several meters. The oceans of the Jurassic teemed with life as well. Marine reptiles, including ichthyosaurs, plesiosaurs, and marine crocodiles, filled the ecological roles that would later be occupied by whales and dolphins. Ichthyosaurs were particularly well adapted to marine life, with streamlined bodies, large eyes for hunting in deep water, and tail fins that propelled them through the water with powerful strokes. The supercontinent Pangaea continued to break apart during the Jurassic. The Atlantic Ocean began to open as North America and Europe drifted away from Africa and South America. This breakup had important consequences for climate and life, as new ocean basins altered circulation patterns and created new coastal environments. The climate remained warm, with no polar ice caps and relatively high sea levels. The Cretaceous period, the final period of the Mesozoic, lasted from about 145 to 66 million years ago. It was the longest period of the Mesozoic and saw some of the most significant developments in the history of life, including the evolution of flowering plants and the continued diversification of dinosaurs and other groups. The evolution of flowering plants, or angiosperms, was one of the most important biological events of the Cretaceous. Flowering plants had appeared by the early Cretaceous, but they diversified rapidly during the Middle and Late Cretaceous, eventually becoming the dominant form of vegetation on land. Today, flowering plants account for the vast majority of plant species, and they form the foundation of most terrestrial ecosystems. The success of flowering plants was due in part to their reproductive innovations. Flowers attract pollinators, animals that carry pollen from one plant to another, ensuring cross-fertilization. Fruits protect seeds and aid in their dispersal, often by attracting animals that eat the fruit and deposit the seeds elsewhere. These innovations allowed flowering plants to reproduce more efficiently and to colonize new habitats more rapidly than their competitors. The spread of flowering plants had cascading effects throughout the ecosystem. New food sources became available for herbivorous insects, which diversified in response. The insects, in turn, provided food for insectivorous animals, including many birds and small mammals. The coevolution of flowering plants and their pollinators and seed dispersers created complex webs of ecological relationships that persist to this day. The dinosaurs of the Cretaceous were diverse and spectacular. In North America, the late Cretaceous saw the evolution of some of the most famous dinosaurs, including Tyrannosaurus rex, the apex predator of its time. Tyrannosaurus was one of the largest land predators ever to exist, reaching lengths of over 12 meters and weights of perhaps 8,000 kilograms or more. Its massive skull housed jaws lined with teeth the size of bananas, capable of crushing bone and tearing through flesh. Other notable Cretaceous dinosaurs included Triceratops, a large herbivore with 3 horns and a bony frill that may have been used for defense or display. Velociraptor and its relatives, small but intelligent predators that may have hunted in packs, and the hadrosaurs or duck-billed dinosaurs, herbivores with specialized teeth for grinding plant material. The diversity of dinosaurs during the Cretaceous was remarkable, with species adapted to almost every conceivable ecological role. The pterosaurs reached their largest sizes during the Cretaceous. Quetzalcoatlus, discovered in Texas, had a wingspan of perhaps 10 to 11 meters, making it one of the largest flying animals ever to exist. These giant pterosaurs probably spent much of their time on the ground, walking on all fours and using their long necks to forage for food, perhaps like enormous reptilian storks. The marine reptiles of the Cretaceous were equally impressive. Mosasaurs, a group of marine lizards related to modern monitor lizards and snakes, became the dominant marine predators of the late Cretaceous. Some mosasaurs reached lengths of 15 meters or more, with powerful jaws and streamlined bodies that made them formidable hunters. Plesiosaurs also continued to thrive, with some species developing extremely long necks that may have been used to ambush fish and other prey. The continents continued to drift toward their modern positions during the Cretaceous. The Atlantic Ocean widened as the Americas moved away from Europe and Africa. India, which had been part of the southern supercontinent Gondwana, broke away and began its long journey northward, eventually colliding with Asia and raising the Himalayas. Australia and Antarctica remained connected, though they would separate in the following era. The climate of the Cretaceous was generally warm, with no polar ice caps for most of the period. Sea levels were high, flooding large portions of the continents and creating shallow seas like the Western Interior Seaway, which divided North America into two landmasses. These warm, shallow seas were productive environments, supporting diverse communities of marine life. But the Cretaceous period and the entire Mesozoic era came to a sudden and catastrophic end 66 million years ago. This was the Cretaceous-Paleogene extinction event, often abbreviated as the KPG extinction, which eliminated the non-avian dinosaurs and many other groups of organisms. It is one of the most studied events in Earth's history, and its cause is now well established. The KPG extinction was triggered by the impact of a large asteroid or comet, roughly 10 to 15 kilometers in diameter, which struck what is now the Yucatan Peninsula of Mexico. The impact created the Chicxulub crater, a structure about 180 kilometers in diameter that is now buried beneath younger sediments, but has been detected through geological surveys. The immediate effects of the impact were devastating. The energy released was equivalent to billions of nuclear weapons detonating simultaneously. A massive fireball incinerated everything within hundreds of kilometers of the impact site. Tsunamis hundreds of meters high swept across the Gulf of Mexico and the Atlantic Ocean. Earthquakes far more powerful than any in recorded human history shook the entire planet. But the long-term effects were even more destructive. The impact ejected enormous quantities of dust and debris into the atmosphere, blocking sunlight and plunging the world into a prolonged period of darkness and cold. Photosynthesis shut down, collapsing food chains on land and in the sea. Wildfires, ignited by the rain of hot debris falling back from the sky, swept across continents. Acid rain, formed from sulfur released by the impact, poisoned soils and surface waters. The extinction was not instantaneous, but it was geologically rapid. Within perhaps a few years to a few tens of thousands of years, the non-avian dinosaurs were gone, along with the pterosaurs, the marine reptiles, the ammonites, and many other groups. An estimated 75% of all species on Earth went extinct, ending the Mesozoic era and the 165 million year reign of the dinosaurs. The KPG extinction was a tragedy of almost incomprehensible proportions. The elimination of countless species that had evolved over hundreds of millions of years. And yet, as with all mass extinctions, it was also an opportunity. The ecological niches left vacant by the dinosaurs and other extinct groups were now available for new occupants. The survivors of the catastrophe, those fortunate few that had managed to endure the darkness and cold and devastation, found themselves in a world of possibilities. Among the survivors were the birds, the only dinosaurs to make it through the extinction. These feathered descendants of theropod dinosaurs had already diversified during the Cretaceous, and they would continue to evolve and spread in the aftermath of the impact. Today, with over 10,000 species, birds are among the most successful groups of vertebrates on Earth, a living reminder that the age of dinosaurs never truly ended. Also, among the survivors were the mammals, small and unassuming creatures that had lived in the shadow of the dinosaurs for over 150 million years. During the Mesozoic, mammals had been mostly small nocturnal animals, filling ecological roles similar to those of modern rodents and shrews. They had been held in check by the dinosaurs, unable to evolve to large sizes or to occupy the ecological niches dominated by their reptilian overlords. But with the dinosaurs gone, the mammals were free to diversify as never before. Within just a few million years of the Cape Age extinction, mammals had evolved to fill many of the niches left vacant by the dinosaurs. Large herbivores, large predators, flying forms, swimming forms, burrowing forms, all of these appeared in rapid succession as mammals underwent an explosive, adaptive radiation. The Cenozoic era, the era of recent life, would be the age of mammals. Let your body sink even deeper into relaxation as we leave the Mesozoic behind. The age of dinosaurs has ended, but the story of Earth continues. The world that emerged from the ashes of the Cape Age extinction would be very different from what came before. A world shaped by mammals and birds, by flowering plants and grasses, by the continued drift of continents and the rise and fall of ice ages. The stage is set for the final chapters of our journey, the chapters that will eventually lead to us. Section 8, the Cenozoic era, the rise of mammals. We now enter the Cenozoic era, the era of recent life, which began 66 million years ago and continues to the present day. This is the era in which we live, the era that has shaped the world we know. During the Cenozoic, mammals diversified into the dominant land animals. Birds continued their evolutionary success. Flowering plants came to dominate terrestrial vegetation, and the continents drifted into their modern positions. It is also the era that saw the evolution of our own species, Homo sapiens, though that story will be told in a later section. The Cenozoic is divided into three periods: the Paleogene, lasting from 66 to 23 million years ago, the Neogene, lasting from 23 to 2.6 million years ago, and the Quaternary, lasting from 2.6 million years ago to the present. These periods are further divided into epochs, each with its own distinctive character and fauna. The early Cenozoic, particularly the Paleocene and Eocene epochs, was a time of recovery and rapid evolution. The world was still warm, with no polar ice caps and tropical forests extending to high latitudes. The continents were arranged somewhat differently than they are today, with Australia still connected to Antarctica and India just beginning its collision with Asia. In this warm, forested world, mammals diversified at an astonishing rate. Within the first 10 million years of the Cenozoic, most of the major groups of mammals that exist today had appeared, including primates, rodents, carnivores, hoofed mammals, and many others. Some early mammals evolved to large sizes remarkably quickly, filling the ecological roles left vacant by the dinosaurs. The Paleocene epoch, lasting from 66 to 56 million years ago, saw the first wave of mammalian diversification. The mammals of the Paleocene were generally archaic forms, not directly ancestral to most modern groups, but representing early experiments in mammalian evolution. Many were small, generalized creatures, but some grew to respectable sizes. Titanoides, for example, was a bear-sized mammal with powerful claws, possibly used for digging or for defense. The Eocene epoch, lasting from 56 to 34 million years ago, was perhaps the warmest period of the entire Cenozoic. Global temperatures peaked during the early Eocene, with average temperatures perhaps 10 to 15 degrees Celsius warmer than today. Palm trees grew in Alaska, and crocodiles basked on the shores of the Arctic Ocean. This warm, equable climate allowed tropical and subtropical forests to spread across much of the globe. The mammals of the Eocene were more modern in aspect than those of the Paleocene. The first true primates appeared, small tree-dwelling creatures with grasping hands and forward-facing eyes. The first members of the horse family evolved, tiny animals no larger than a small dog, with multiple toes on each foot rather than the single hoof of modern horses. The first whales appeared, descendants of land-dwelling mammals that had returned to the sea. The evolution of whales is one of the most remarkable stories in mammalian history. The ancestors of whales were small four-legged mammals that lived near the shores of the ancient Tethys Sea, which separated the northern and southern continents. Over millions of years, these animals became increasingly adapted to aquatic life, their legs shrinking into flippers, their bodies becoming streamlined, their nostrils migrating to the top of the head to form blowholes. Fossils from Pakistan and Egypt have revealed the transitional forms in whale evolution, animals like Pachycetus, Ambulocetus, and Basilosaurus, that show the gradual transformation from land-dwelling mammal to fully aquatic whale. Pachycetus, from about 50 million years ago, was a wolf-sized animal that probably spent most of its time on land, but hunted in shallow water. Ambulocetus, from a few million years later, was more aquatic, with large paddle-like feet and a long crocodile-like snout. Basilosaurus, from about 40 million years ago, was fully aquatic, with a long serpentine body and tiny vestigial hind limbs. The Eocene also saw the evolution of the first bats, the only mammals capable of true powered flight. Bats probably evolved from small tree-dwelling insectivores that developed the ability to glide between trees, then gradually evolved the wing membranes and flight muscles necessary for sustained flight. The oldest known bat fossils, from about 52 million years ago, already show fully developed wings, suggesting that the evolution of flight occurred relatively rapidly. The warm climates of the Eocene began to cool toward the end of the epoch, a trend that would continue through much of the rest of the Cenozoic. The causes of this cooling were complex, involving changes in ocean circulation, the weathering of newly uplifted mountain ranges, and the drawdown of atmospheric carbon dioxide. By the end of the Eocene, about 34 million years ago, the cooling had progressed far enough that ice sheets began to form on Antarctica for the first time since the Permian. The Oligocene epoch, lasting from 34 to 23 million years ago, saw continued cooling and the spread of more open habitats. The tropical forests that had covered much of the globe during the Eocene began to shrink, replaced by woodlands, savannas, and grasslands. This change in vegetation had profound effects on mammalian evolution, favouring animals adapted to more open environments. The horses provide a classic example of evolutionary response to changing habitats. The small multi-toed horses of the Eocene were adapted to life in forests, browsing on soft leaves and fruits. As grasslands spread during the Oligocene and Miocene, horses evolved larger bodies, longer legs for running across open terrain, and high-crowned teeth capable of grinding the tough, silica-rich grasses. The single-toed hoof of modern horses evolved as an adaptation for efficient running on hard ground. The Miocene epoch, lasting from 23 to 5.3 million years ago, was a time of continued mammalian diversification and the spread of grasslands. The climate was generally warmer than today, though cooler than the Eocene, and grasslands became increasingly dominant in many parts of the world. This was the heyday of many mammalian groups, including horses, rhinoceroses, elephants, and the first apes. The apes, the group that includes humans and our closest relatives, first appeared during the Miocene. Early apes were forest-dwelling creatures, similar in many ways to modern gibbons and orangutans. They had large brains relative to their body size, flexible shoulders, and wrists adapted for swinging through trees, and no tails. From these early apes would eventually evolve the great apes, including chimpanzees, gorillas, and humans. The Miocene also saw the evolution of many familiar groups of carnivores. The first true cats appeared, including both the ancestors of modern cats and the famous saber-toothed cats, which would become apex predators in many ecosystems. Dogs, bears, and weasels also diversified during the Miocene, filling a variety of ecological roles, from small insectivores to large pack-hunting predators. The Pliocene epoch, lasting from 5.3 to 2.6 million years ago, saw continued cooling and the approach of the ice ages. The climate became increasingly seasonal, with colder winters and more pronounced differences between high and low latitudes. The grasslands that had spread during the Miocene continued to expand, and many mammalian lineages adapted to these open habitats. It was during the Pliocene that the first members of our own genus, Homo, may have appeared. Though the fossil record from this time is fragmentary, and the exact timing of human origins remains debated, what is clear is that by the end of the Pliocene, our ancestors had evolved many of the features that distinguish humans from other apes, including upright walking, reduced canine teeth, and the beginnings of increased brain size. The Pliocene also saw a significant geological event, the formation of the Isthmus of Panama, which connected North and South America for the first time in tens of millions of years. This land bridge allowed animals to migrate between the two continents, an event known as the Great American Interchange. North American animals like horses, camels, and cats moved south, while South American animals like armadillos, opossums, and ground sloths moved north. The Great American Interchange had profound effects on the faunas of both continents. Many South American mammals, which had evolved in isolation for millions of years, were unable to compete with the invaders from the north and went extinct. The native South American predators, including large flightless birds and marsupial carnivores, were replaced by cats, dogs, and bears from North America. The interchange reshaped the ecosystems of both continents and contributed to the distinctive mix of animals found in the Americas today. The Quaternary period, the final period of the Cenozoic, began about 2.6 million years ago and continues to the present. This period is characterized by repeated glaciations, cycles of ice ages, and warmer interglacial periods that have profoundly shaped the modern world. We are currently living in an interglacial period, a relatively warm interval between ice ages, though human activities are now altering the climate in ways that may disrupt these natural cycles. The ice ages of the Quaternary were driven by subtle variations in Earth's orbit around the Sun, known as Milankovitch cycles. These cycles affect the amount and distribution of solar energy reaching Earth's surface, triggering the growth and retreat of ice sheets over periods of tens of thousands of years. At their maximum extent, ice sheets covered much of North America and northern Europe, reaching as far south as present-day New York and London. The ice ages had profound effects on life. Many animals evolved adaptations to cold climates, including thick fur, large body sizes, and the ability to hibernate or migrate. The famous megafauna of the Ice Ages, including woolly mammoths, woolly rhinoceroses, giant ground sloths, and saber-toothed cats, were adapted to the cold, open landscapes of the glacial periods. The Ice Ages also affected sea levels, which dropped dramatically as water was locked up in glaciers. At the peak of the last Ice Age, about 20,000 years ago, sea levels were roughly 120 metres lower than they are today. This exposed vast areas of continental shelf, creating land bridges that allowed animals, including humans, to migrate between continents. The Bering Land Bridge, connecting Asia and North America, allowed humans to enter the Americas for the first time. The megafauna of the Ice Ages began to disappear toward the end of the Pleistocene epoch, in a wave of extinctions that coincided with the spread of humans across the globe. Woolly mammoths, mastodons, giant ground sloths, saber-toothed cats, and many other large animals went extinct between about 50,000 and 10,000 years ago. The causes of these extinctions are still debated, but most scientists believe that human hunting, combined with climate change at the end of the Ice Age, played a significant role. The Holocene epoch, which began about 11,700 years ago, is the current geological epoch. It is characterized by relatively stable, warm climate conditions that have allowed human civilizations to flourish. During the Holocene, humans developed agriculture, built cities, and transformed the planet in ways that no other species has ever done. The Cenozoic era has been a time of remarkable change and diversification. From the small shrew-like mammals that survived the Cape Age extinction to the whales, elephants, and primates of today, mammals have evolved to fill almost every ecological niche on Earth. Birds have continued their success, diversifying into over 10,000 species. Flowering plants have come to dominate terrestrial vegetation, and the continents have drifted into their modern positions. And through it all, one lineage of mammals has been on a remarkable evolutionary journey, developing larger brains, more sophisticated tools, and eventually the capacity for language, art, and science. That lineage is our own, and its story deserves a section of its own. Let your breathing slow and your body relax as we prepare to explore the evolution of humans, the most recent chapter in the long history of life on Earth. The story is nearing its end, but some of the most remarkable developments are still to come. Section 9. The Age of Humans. We now turn to the story of our own species, Homo sapiens, and the broader lineage of human ancestors and relatives known as hominins. This is a story that spans roughly 7 million years, from the time when our ancestors diverged from the ancestors of chimpanzees to the present day. It is a story of gradual transformation, of the evolution of upright walking, tool use, large brains, and eventually language and culture. It is in many ways the most personal chapter of Earth's history, for it is the story of how we came to be. The study of human evolution has been revolutionized in recent decades by new fossil discoveries, advances in dating techniques, and the development of ancient DNA analysis. We now have a much more detailed picture of our evolutionary history than was available even a few decades ago, though many questions remain unanswered and new discoveries continue to reshape our understanding. The human lineage diverged from the lineage leading to chimpanzees and bonobos sometime between about 7 and 6 million years ago, during the late Miocene epoch. The exact timing and circumstances of this split are still debated, but it probably occurred in Africa, where both humans and African apes have their evolutionary roots. The earliest known hominins, the group that includes humans and our ancestors, after the split from chimpanzees, are fragmentary and controversial. Sahelanthropus chadensis, known from a skull found in Chad and dated to about 7 million years ago, may be one of the earliest hominins, though some scientists argue it may be an ancestor of gorillas or a member of some other lineage. Tugenensis from Kenya, and dated to about 6 million years ago, shows some features suggesting upright walking, a key hominin characteristic. By about 4 million years ago, hominins had become more diverse and better represented in the fossil record. The genus Australopithecus, meaning southern ape, includes several species that lived in Africa between about 4 and 2 million years ago. These were small-brained creatures with brain sizes similar to those of modern chimpanzees, but they walked upright on 2 legs, a form of locomotion called bipedalism. The most famous Australopithecus fossil is Lucy, a remarkably complete skeleton of Australopithecus afarensis discovered in Ethiopia in 1974. Lucy lived about 3.2 million years ago and stood only about 1 metre tall. Her skeleton shows a mix of ape-like and human-like features, a small brain, long arms, and curved fingers suggesting she still spent time in trees, but also a pelvis and leg bones adapted for upright walking. Why did our ancestors evolve to walk upright? This question has been debated for over a century, and no single answer has gained universal acceptance. Possible advantages of bipedalism include the ability to see over tall grass, freeing the hands for carrying food or tools, more efficient long-distance travel, and reduced exposure to the hot tropical sun. Whatever the reasons, bipedalism was established early in hominin evolution and became a defining characteristic of our lineage. The Australopithecines were successful for over 2 million years, diversifying into several species adapted to different environments and diets. Some, like Australopithecus africanus, had relatively generalized diets and may have eaten a variety of fruits, leaves, and other plant foods. Others, like Paranthropus boisei, developed massive jaws and teeth adapted for processing tough, fibrous plant foods, like roots and tubers. Around 2.8 to 2.5 million years ago, a new kind of hominin appeared in Africa, the first members of our own genus, Homo. The earliest Homo species, such as Homo habilis, had larger brains than the Australopithecines and were associated with the first stone tools. These early tools, known as Oldowan tools after Olduvai Gorge in Tanzania, where they were first discovered, were simple but effective, consisting of sharp flakes struck from larger cobbles. The evolution of tool use was a crucial development in human history. Tools allowed our ancestors to access new food sources, such as meat from large animals and marrow from bones. They provided advantages in competition with other species and may have contributed to the expansion of the brain, as the cognitive demands of tool-making and use selected for increased intelligence. Homo erectus, which appeared about 1.9 million years ago, was the first hominin to spread beyond Africa. Homo erectus had a larger brain than earlier Homo species, a more modern body plan with long legs and short arms, and more sophisticated tools. Fossils of Homo erectus have been found across Africa, Europe and Asia, from Spain to Indonesia, indicating that this species was highly successful and adaptable. Homo erectus was also the first hominin to control fire, though the timing of this development is debated. Evidence of controlled fire use dates back at least 400,000 years, and possibly much earlier. Fire provided warmth, protection from predators, and the ability to cook food. Cooking made food easier to digest and may have contributed to the continued expansion of the brain, which requires large amounts of energy. The period from about 800,000 to 200,000 years ago saw the evolution of several hominin species with increasingly large brains. In Africa, Homo heidelbergensis evolved, a species with a brain size approaching that of modern humans. In Europe, Homo heidelbergensis gave rise to the Neanderthals, our closest known relatives, who were adapted to the cold climates of Ice Age Europe. The Neanderthals were sophisticated humans in many ways. They had brains as large as or larger than those of modern humans. They made complex stone tools, controlled fire, and may have used language. They buried their dead, suggesting some form of symbolic or spiritual behavior. They survived in Europe for over 300,000 years, enduring multiple ice ages and adapting to some of the harshest conditions faced by any hominin. Our own species, Homo sapiens, evolved in Africa sometime between about 300,000 and 200,000 years ago. The oldest known fossils of Homo sapiens come from Jebel Irhoud in Morocco, dated to about 300,000 years ago, and from Omo Kibish in Ethiopia, dated to about 195,000 years ago. These early Homo sapiens had the characteristic features of our species: a high, rounded skull, a flat face, and a chin. For most of our species' existence, Homo sapiens lived in Africa, developing increasingly sophisticated tools, art, and culture. The earliest evidence of symbolic behavior, including the use of pigments and the creation of decorative objects, dates back over 100,000 years in Africa. By about 70,000 years ago, Homo sapiens had developed the full suite of behaviors that characterize modern humans, including complex language, art, music, and religion. Around 70,000 to 50,000 years ago, Homo sapiens began to spread out of Africa, eventually colonizing every continent except Antarctica. This expansion brought our ancestors into contact with other hominin species, including the Neanderthals in Europe and the Denisovans in Asia. These encounters sometimes resulted in interbreeding, and most people of non-African descent carry small amounts of Neanderthal DNA in their genomes. The spread of Homo sapiens across the globe was remarkably rapid by evolutionary standards. By 50,000 years ago, humans had reached Australia, crossing open ocean to do so. By 15,000 years ago, humans had entered the Americas, probably via the Bering Land Bridge that connected Asia and North America during the last ice age. By 1,000 years ago, humans had reached even the most remote Pacific islands, completing the colonization of the habitable world. Wherever humans went, they transformed the environment. The megafauna extinctions of the late Pleistocene coincided with the arrival of humans on each continent, suggesting that human hunting played a role in these extinctions. Humans also modified landscapes through fire, clearing forests and creating grasslands that favoured the animals they hunted. The development of agriculture, beginning about 10,000 to 12,000 years ago, was perhaps the most significant transformation in human history. Agriculture allowed humans to produce more food from a given area of land, supporting larger populations and enabling the development of permanent settlements, cities, and eventually civilizations. The domestication of plants and animals fundamentally changed the relationship between humans and the natural world. The rise of civilizations brought new developments: writing, mathematics, science, and technology. Humans learned to smelt metals, build monuments, and wage wars on unprecedented scales. The pace of change accelerated, with each generation building on the knowledge and achievements of those that came before. The Industrial Revolution, beginning about 250 years ago, marked another fundamental transformation. The harnessing of fossil fuels provided vast amounts of energy, powering machines that could do the work of hundreds of humans. Populations grew, cities expanded, and human impact on the environment increased dramatically. Today, humans are the dominant species on Earth, with a population of over 8 billion and an influence that extends to every corner of the globe. We have transformed landscapes, altered the composition of the atmosphere, and driven countless species to extinction. We have also developed the capacity to understand our own history, to peer back through billions of years of Earth's past and to contemplate our place in the cosmos. The story of human evolution is, in many ways, the story of increasing power and influence. From small, vulnerable primates on the African savanna, we have become a force capable of reshaping the planet. This power brings with it tremendous responsibility, for the choices we make today will determine the future of Earth and all its inhabitants. As you rest and relax, consider the remarkable journey that has brought us to this moment. From the first simple cells in the Archean oceans, through billions of years of evolution and extinction, through the rise and fall of countless species, life has persisted and diversified. And now, for the first time in Earth's history, one species has developed the capacity to understand this journey, to appreciate its beauty and complexity, and to take responsibility for its future. Let your breathing slow and your body sink deeper into relaxation as we move into the final sections of our journey, exploring the dynamic systems that make Earth habitable and contemplating our planet's place in the cosmos. Section 10, Earth's Dynamic Systems. Throughout our journey through Earth's history, we have touched on many of the processes that shape our planet: volcanism, plate tectonics, the water cycle, the evolution of the atmosphere. In this section, we will explore these dynamic systems in more depth, understanding how they work together to create the habitable world we know today. Earth is not a static world. It is constantly changing, driven by energy from within and from without. The interior of the Earth is still hot, heated by the decay of radioactive elements and by the residual heat from the planet's formation. This internal heat drives the motion of tectonic plates, the eruption of volcanoes, and the generation of Earth's magnetic field. Energy from the sun drives the climate system, the water cycle, and the growth of plants through photosynthesis. These energy sources interact in complex ways, creating the dynamic, ever-changing planet we call home. Plate tectonics is perhaps the most fundamental of Earth's dynamic systems. The outer layer of the Earth, called the lithosphere, is divided into a dozen or so large plates and many smaller ones. These plates float on the underlying asthenosphere, a layer of hot, partially molten rock that flows slowly over geological timescales. The plates move relative to each other, driven by convection currents in the mantle and by the pull of gravity on subducting plates. At divergent boundaries, plates move apart. A new lithosphere is created as magma rises from the mantle to fill the gap. The mid-ocean ridges, underwater mountain ranges that wind through all the world's oceans, are divergent boundaries where new oceanic crust is constantly being formed. Iceland, which straddles the mid-Atlantic ridge, is one of the few places where a divergent boundary rises above sea level, and the island is being slowly torn apart as the North American and Eurasian plates move away from each other. At convergent boundaries, plates move toward each other, and one plate is typically forced beneath the other in a process called subduction. Subduction zones are marked by deep ocean trenches, chains of volcanoes, and frequent earthquakes. The Pacific Ring of Fire, which encircles the Pacific Ocean, is a zone of intense volcanic and seismic activity associated with the subduction of oceanic plates beneath continental plates. When two continental plates collide, neither can be subducted because continental crust is too buoyant. Instead, the crust crumples and folds, creating mountain ranges. The Himalayas, the highest mountains on Earth, were formed by the collision of the Indian and Eurasian plates, a collision that began about 50 million years ago and continues today. The Alps, the Pyrenees, and many other mountain ranges were formed by similar continental collisions. At transform boundaries, plates slide past each other horizontally, neither creating nor destroying lithosphere. The San Andreas Fault in California is a famous transform boundary, where the Pacific plate is sliding northward relative to the North American plate. Transform boundaries are associated with frequent earthquakes, but little volcanic activity. Plate tectonics has shaped Earth's surface throughout its history, assembling and breaking apart supercontinents, opening and closing ocean basins, and creating the mountains and valleys that define our landscapes. The continents we know today are just the latest configuration in a long history of continental drift. In the future, the continents will continue to move, eventually assembling into a new supercontinent that scientists have named Pangaea Proxima or Amasia. Volcanism is another fundamental process shaping Earth's surface. Volcanoes occur primarily at plate boundaries, where the movement of plates creates conditions favourable for magma generation. At divergent boundaries, the separation of plates allows hot mantle rock to rise and melt, creating the basaltic magmas that form new oceanic crust. At convergent boundaries, the subduction of oceanic crust releases water into the overlying mantle, lowering the melting point and generating the magmas that feed volcanic arcs. Volcanoes also occur at hotspots, locations where plumes of hot mantle rock rise from deep within the Earth. The Hawaiian Islands are the most famous example of hotspot volcanism. As the Pacific Plate moves over the stationary hotspot, new volcanoes form, creating a chain of islands that stretches across the Pacific. The Big Island of Hawaii, with its active volcanoes Kilauea and Mauna Loa, is currently over the hotspot, while the older islands to the northwest have moved away and are slowly eroding. Volcanic eruptions can be gentle or catastrophic, depending on the composition of the magma and the amount of dissolved gas it contains. Basaltic magmas, which are relatively fluid and low in dissolved gas, tend to produce gentle eruptions with flowing lava. Silica-rich magmas, which are more viscous and contain more dissolved gas, tend to produce explosive eruptions that can hurl ash and rock high into the atmosphere. The largest volcanic eruptions can have global effects. The eruption of Mount Tambora in Indonesia in 1815 ejected so much ash and sulfur dioxide into the atmosphere that it caused the year without a summer in 1816, with crop failures and famine across Europe and North America. Even larger eruptions, like those that created the Siberian traps at the end of the Permian, can trigger mass extinctions by altering the climate and chemistry of the atmosphere and oceans. Earth's magnetic field is another crucial dynamic system, generated by the motion of liquid iron in the outer core. This motion, driven by convection and the rotation of the Earth, creates a self-sustaining dynamo that generates a magnetic field extending far into space. The magnetic field protects Earth from the solar wind, a stream of charged particles constantly flowing from the Sun. Without the magnetic field, the solar wind would gradually strip away Earth's atmosphere, as it has done on Mars. The magnetic field is not constant. It varies in strength over time, and it occasionally reverses polarity, with the north and south magnetic poles switching places. These reversals occur irregularly, sometimes separated by millions of years, and sometimes by only tens of thousands of years. The last reversal occurred about 780,000 years ago, and we are currently in a period of normal polarity. The reversals are recorded in the volcanic rocks, which preserve the orientation of the magnetic field at the time they cooled, providing a valuable tool for dating and correlating rock sequences. The atmosphere is another dynamic system, constantly circulating and exchanging gases with the oceans, the land surface, and living organisms. The composition of the atmosphere has changed dramatically over Earth's history, from the carbon dioxide and nitrogen-dominated atmosphere of the early Earth to the oxygen-rich atmosphere we breathe today. These changes have been driven by geological processes such as volcanic outgassing and the weathering of rocks, and by biological processes such as photosynthesis and respiration. The modern atmosphere is composed primarily of nitrogen, about 78%, and oxygen, about 21%, with smaller amounts of argon, carbon dioxide, water vapour, and trace gases. The oxygen in the atmosphere is almost entirely the product of photosynthesis produced by plants, algae, and cyanobacteria over billions of years. Without photosynthesis, the oxygen would be consumed by reactions with rocks and organic matter, and the atmosphere would return to an oxygen-free state within a few million years. The atmosphere plays a crucial role in regulating Earth's temperature through the greenhouse effect. Greenhouse gases, including carbon dioxide, water vapour, methane, and nitrous oxide, absorb infrared radiation emitted by Earth's surface and re-radiate it in all directions, including back toward the surface. This traps heat in the lower atmosphere, keeping Earth's surface warm enough for liquid water to exist. Without the greenhouse effect, Earth's average surface temperature would be about -18 degrees Celsius, well below the freezing point of water. The natural greenhouse effect raises the average temperature to about 15 degrees Celsius, making Earth habitable. However, human activities are now increasing the concentration of greenhouse gases in the atmosphere, enhancing the greenhouse effect and causing global warming. The water cycle is another fundamental dynamic system, driven by energy from the sun. Water evaporates from the oceans, lakes, and land surfaces, rises into the atmosphere, condenses into clouds, and falls back to the surface as precipitation. This cycle moves vast amounts of water around the planet, shaping landscapes through erosion and deposition, and providing the fresh water that terrestrial life depends on. The oceans play a crucial role in the water cycle and in regulating Earth's climate. They absorb heat from the sun, storing it and releasing it slowly, which moderates temperature extremes. Ocean currents transport heat from the tropics toward the poles, influencing climate patterns around the world. The oceans also absorb carbon dioxide from the atmosphere, helping to regulate the greenhouse effect. Though this absorption is causing ocean acidification, which threatens marine ecosystems. The carbon cycle connects the atmosphere, oceans, land surface, and living organisms in a complex web of exchanges. Carbon moves between these reservoirs through processes such as photosynthesis, respiration, decomposition, volcanic outgassing, and the weathering of rocks. Over geological timescales, the carbon cycle has regulated atmospheric carbon dioxide levels and, through the greenhouse effect, Earth's climate. Living organisms are integral to many of Earth's dynamic systems. Plants and photosynthetic microorganisms produce the oxygen we breathe and remove carbon dioxide from the atmosphere. Animals and decomposers return carbon dioxide to the atmosphere through respiration and decomposition. The activities of living organisms have transformed Earth's atmosphere, oceans, and land surfaces over billions of years, creating the habitable planet we know today. These dynamic systems are interconnected in complex ways, with changes in one system affecting others. The rise of oxygen in the atmosphere, for example, was driven by photosynthetic organisms, but it also affected the chemistry of the oceans, the weathering of rocks, and the evolution of life. The movement of tectonic plates affects ocean circulation, which affects climate, which affects the distribution of life. Understanding these interconnections is crucial for understanding how Earth works and how it might respond to future changes. As you rest and relax, consider the remarkable complexity of the planet we call home. Earth is not just a ball of rock orbiting a star. It is a dynamic, interconnected system, constantly changing and evolving, shaped by processes operating over timescales from seconds to billions of years. The air you breathe, the water you drink, the ground beneath your feet, all of it is part of this vast, intricate system, a system that has been operating for over 4.5 billion years and will continue long after we are gone. Let your breathing slow and your body sink deeper into relaxation as we move into the final sections of our journey, contemplating Earth's place in the cosmos and its future. Section 11, Earth Today and its place in the cosmos. We have travelled through billions of years of Earth's history, from the formation of our planet in a disk of gas and dust around the young sun to the present day. Now, let us pause and consider the world as it exists in this very moment, and contemplate its place in the vast expanse of the universe. For Earth is not just a planet with a history, it is a world that exists right now, spinning through space, orbiting a star, part of a galaxy, part of a universe so immense that the human mind can scarcely comprehend it. As you rest and breathe slowly, let yourself feel the gentle motion of the Earth beneath you. You cannot perceive it directly, but our planet is rotating on its axis at over 1,600 kilometers per hour at the equator, completing one full rotation every 24 hours. This rotation gives us day and night, the endless cycle of light and darkness that has governed life on Earth since the first organisms evolved to sense the sun. At the same time, Earth is orbiting the sun at a speed of about 107,000 kilometers per hour, completing one full orbit every 365.25 days. This orbital motion, combined with the tilt of Earth's axis, gives us the seasons, the annual rhythm of warmth and cold, growth and dormancy that shapes ecosystems and human cultures around the world. But our motion does not stop there. The Sun itself is moving through the Milky Way galaxy, carrying Earth and all the other planets along with it. Our solar system orbits the centre of the galaxy at a speed of about 828,000 kilometers per hour, completing one full orbit every 230 million years or so. Since Earth formed 4.5 billion years ago, our planet has completed roughly 20 orbits around the galactic centre, each orbit a galactic year in the life of our world. And the Milky Way itself is moving through the universe, drawn by the gravity of other galaxies and the vast structures of the cosmic web. We are part of a group of galaxies called the Local Group, which includes the Andromeda Galaxy, about 2.5 million light-years away, and dozens of smaller galaxies. The Local Group is part of a larger structure called the Virgo Supercluster, and the Virgo Supercluster is part of an even larger structure called Laniakea, a supercluster containing over 100,000 galaxies. When we consider Earth's cosmic address, we begin to appreciate just how small and precious our world truly is. Earth is located in one of the spiral arms of the Milky Way, called the Orion Arm, which lies about 2/3 of the way out from the centre of the galaxy. Here, in this relatively quiet corner of the galaxy, far from the intense radiation and gravitational chaos near the galactic centre, conditions have been stable enough for life to evolve and flourish over billions of years. Our Sun is just one of an estimated 100 to 400 billion stars in the Milky Way galaxy, and the Milky Way is just one of an estimated 2 trillion galaxies in the observable universe. The numbers are so vast that they lose meaning, becoming abstract figures rather than quantities we can truly comprehend. And yet in all this immensity, Earth remains the only place we know of where life exists. This is what makes our planet so extraordinary. In a universe filled with stars and galaxies, with planets and moons beyond counting, Earth is the only world where we have found living organisms. It is a tiny, fragile exception. In the cosmos, a pale blue dot suspended in a sunbeam, as Carl Sagan so memorably described it. What makes Earth so special? Why has life flourished here when, as far as we know, it has not flourished elsewhere? The answer lies in a remarkable combination of factors, some of which we have explored throughout our journey, and some of which we will consider now. Earth sits in our Sun's habitable zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Too close to the Sun, and water would boil away into space. Too far, and water would freeze solid. Earth occupies a sweet spot, a Goldilocks zone where water can exist in all three phases: solid, liquid, and gas. But the habitable zone is just the beginning. Many factors have contributed to Earth's habitability, and the absence of any one of them might have made our planet as barren as Mars, or as hellish as Venus. Earth's size is important. Our planet is large enough to have significant gravity, which allows it to retain a substantial atmosphere. Smaller planets like Mars have weaker gravity and have lost much of their atmosphere to space over billions of years. Earth's size also means it has enough internal heat to drive plate tectonics and volcanism, processes that recycle carbon and regulate the climate over geological timescales. Earth's magnetic field, generated by the churning liquid iron in its outer core, protects the atmosphere from the solar wind. Without this magnetic shield, the charged particles streaming from the Sun would gradually strip away the atmosphere, as they have done on Mars. The magnetic field deflects most of these particles, channeling them toward the poles where they create the beautiful auroras. Earth's moon, formed in the giant impact early in our planet's history, stabilizes the tilt of Earth's axis. Without the moon, Earth's axial tilt would vary chaotically over millions of years, causing extreme climate swings that might make complex life impossible. The moon's gravitational influence keeps Earth's tilt relatively stable, ensuring that the seasons remain moderate and predictable. The presence of liquid water is perhaps the most crucial factor for life as we know it. Water is an extraordinary substance with properties that make it ideal as a medium for the chemistry of life. It is an excellent solvent, capable of dissolving a wide range of substances and facilitating chemical reactions. It has a high heat capacity, which helps moderate temperature extremes, and it expands when it freezes, so ice floats on liquid water, insulating the water below and preventing lakes and oceans from freezing solid. Earth's atmosphere, with its mix of nitrogen, oxygen, and trace gases, provides the air we breathe and regulates the planet's temperature through the greenhouse effect. The oxygen in the atmosphere, produced by photosynthetic organisms over billions of years, allows for the efficient metabolism that powers complex animal life. The ozone layer, formed from oxygen molecules in the upper atmosphere, blocks harmful ultraviolet radiation from the sun. The carbon cycle, operating over geological timescales, has helped regulate Earth's climate and keep temperatures within a range suitable for life. When the climate warms, weathering of rocks increases, drawing carbon dioxide out of the atmosphere and cooling the planet. When the climate cools, weathering decreases, allowing volcanic emissions to build up carbon dioxide and warm the planet. This natural thermostat has helped keep Earth habitable for billions of years, despite changes in the sun's output and other factors. Life itself has played a crucial role in making Earth habitable. Photosynthetic organisms produce the oxygen in the atmosphere. Plants and microorganisms help regulate the carbon cycle. The activities of living things have transformed Earth's surface, creating soils, shaping landscapes, and influencing the climate. Earth is not just a planet where life exists, it is a planet that has been shaped by life. A world where the living and non-living components are intimately interconnected. Today, Earth is home to an astonishing diversity of life. Scientists have described and named nearly 2 million species, but the total number of species on Earth is estimated to be somewhere between 8 and 10 million, with some estimates ranging even higher. These species occupy every conceivable habitat, from the deepest ocean trenches to the highest mountain peaks, from scorching deserts to frozen polar regions. From the inside of rocks to the bodies of other organisms, the diversity of life on Earth is the product of billions of years of evolution, of countless generations of organisms living, reproducing, and dying, each generation slightly different from the one before. Natural selection, the process by which organisms with advantageous traits are more likely to survive and reproduce, has shaped life into an endless variety of forms, each adapted to its particular environment and way of life. This diversity is not just beautiful, it is essential for the functioning of Earth's ecosystems. Different species play different roles in the web of life, as producers, consumers, decomposers, and recyclers. The loss of species can disrupt these webs, with cascading effects that are often difficult to predict. The current rate of species extinction, driven largely by human activities, is a cause for serious concern, as it threatens to unravel the ecological systems on which we all depend. Earth today is also a planet profoundly shaped by human activities. We have transformed landscapes, converting forests and grasslands to farms and cities. We have altered the composition of the atmosphere, increasing the concentration of carbon dioxide and other greenhouse gases. We have changed the chemistry of the oceans, making them more acidic. We have moved species around the globe, introducing invasive species that disrupt native ecosystems. We have driven countless species to extinction and pushed many more to the brink. The scale of human impact on Earth is so great that many scientists argue we have entered a new geological epoch, the Anthropocene, the age of humans. In this new epoch, human activities are the dominant force shaping the planet, surpassing the natural processes that have governed Earth for billions of years. The decisions we make in the coming decades will determine the future of Earth's climate, ecosystems, and biodiversity for thousands or even millions of years to come. And yet, despite all the challenges we face, Earth remains a world of extraordinary beauty and wonder. The blue of the oceans, the green of the forests, the white of the clouds, the brown and gold of the deserts, all of these colours combine to create a planet unlike any other we have found in the cosmos. From space, Earth appears as a fragile marble, a tiny oasis of life in the vast darkness of space. The famous photograph known as the pale blue dot, taken by the Voyager 1 spacecraft in 1990 from a distance of about 6 billion kilometres, shows Earth as a tiny speck of light, barely visible against the vastness of space. Carl Sagan, who had requested that the photograph be taken, wrote eloquently about what it reveals. You'd look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering. Thousands of confident religions, ideologies and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. These words remind us of both the insignificance and the preciousness of our world. In the vastness of the cosmos, Earth is unimaginably small, and yet it is everything to us. It is the only home we have ever known, the only place in the universe where we are certain that life exists. As we search the cosmos for signs of life elsewhere, we are reminded of how special Earth truly is. Despite decades of searching, we have not yet found definitive evidence of life beyond our planet. We have found planets in the habitable zones of other stars, worlds where liquid water might exist on the surface. We have found organic molecules in interstellar space and on comets and asteroids. We have found environments on other worlds, like the subsurface oceans of Europa and Enceladus, where life might conceivably exist. But we have not yet found life itself. This does not mean that life does not exist elsewhere in the universe. The universe is vast, and our search has barely begun. There may be billions of planets in our galaxy alone, where conditions are suitable for life, and some of them may harbour living organisms. Perhaps some of them even harbour intelligent beings, civilizations that have developed technology and are looking out at the stars, wondering if they are alone. But for now, Earth remains the only world we know of where life has taken hold. This makes our planet infinitely precious, a rare jewel in a universe that, as far as we can tell, is mostly empty and lifeless. It also places a tremendous responsibility on us, the only species on Earth capable of understanding our planet's history and contemplating its future. As you rest and breathe slowly, let yourself feel a sense of connection to this remarkable world. You are made of atoms that were forged in the hearts of ancient stars, atoms that have been part of Earth for billions of years, cycling through rocks and oceans and living things. You are part of the story we have been telling, a story that stretches back to the formation of the solar system and forward into an uncertain but potentially wondrous future. The Earth beneath you is alive, not just with the organisms that cover its surface, but with the dynamic processes that have shaped it for billions of years. The plates are still moving, the volcanoes are still erupting, the mountains are still rising and eroding. The atmosphere is still circulating, the oceans are still flowing, the water cycle is still turning. Life is still evolving, adapting, diversifying, filling every available niche with new forms and new possibilities. And you are part of it all. Every breath you take connects you to the atmosphere, to the plants that produce the oxygen you breathe, to the ancient cyanobacteria that first filled the air with this life-giving gas. Every sip of water connects you to the oceans, to the rivers and lakes, to the rain that falls from the sky and the groundwater that flows beneath your feet. Every bite of food connects you to the soil, to the plants and animals that nourish you, to the web of life that sustains us all. Let this sense of connection bring you peace as we move into the final section of our journey, contemplating the future of Earth and bringing our story to a gentle close.